Hello there and welcome back to the Sleep Science. You've arrived just in time to watch the universe stretch. Not metaphorically, literally. Out there, galaxies are racing away from one another, light stretching like taffy, space itself swelling between everything you've ever known. It's quiet, too quiet, the kind of hush that would make even an introvert nervous. You're drifting through it, weightless, watching the stars slide into deeper reds, the colour of distance. If you could listen close enough, you might swear the cosmos is sighing. And here's the uncomfortable truth. You probably won't survive this, not because of any sudden disaster, but because the timeline of cosmic expansion doesn't care much about your gym schedule. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. I want you to feel welcome, not obligated. Drop your location and your local time in the comments. I love seeing how scattered across the spinning planet we are, tiny observers looking up at the same ancient dark. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You find yourself gliding across a web of galaxies. Imagine thousands of them, each a whirlpool of billions of suns, all caught in motion you can't feel. From here, the pattern looks serene, like cosmic lace, but you know better. It's frantic underneath. Distances between clusters are ballooning. Light from remote quasars takes billions of years just to make eye contact with your telescope. Every second, space itself manufactures more space. It's like a magician pulling an infinite scarf out of nothing, except the scarf is everything. Historians, well, cosmologists, still argue whether the term expansion even does it justice. It's not that galaxies are flying through space like fireworks, it's that space itself is growing. The Milky Way isn't moving through the universe's fabric, it's the fabric that's stretching around it. Einstein's equations predicted something like this long before anyone believed him. When he realized it, he was so unsettled he added a cosmological constant to hold everything still. Later he reportedly called it his biggest blunder, though historians still debate whether he ever said that exact phrase. Either way, irony has a wicked sense of humour. That blunder might describe the very thing that keeps the universe expanding today. You tilt your focus toward a nearby cluster, Virgo maybe. Its galaxies glint like tiny silver coins tossed into a fountain that never stops rippling. The farther you look, the faster they seem to move away. This is not a coincidence. It's the heartbeat of the cosmos. Hubble first measured that rhythm in the 1920s, comparing the speed of galaxies to their distance and realizing the pattern was too clean to ignore. The universe wasn't static, it was inflating, moving outward like bread dough full of rising yeast. Now imagine that same dough billions of years later. The bubbles have grown enormous, and the yeast, dark energy, keeps multiplying. You float between two galaxies that used to be close enough for their gravity to flirt. Now, they're breaking up like old lovers, drifting apart at cosmic miles per second. It's awkward. You want to tell them it's not personal. It's physics. Still, you can sense a strange tension, like the universe is overextending itself. Too much of anything, even expansion, can't last forever. And somewhere deep in that dark fabric, scientists suspect the push might be fading. But not yet. For now, you're suspended in the golden era of cosmic acceleration. Every photon that reaches you is a postcard from a younger universe, one that didn't yet know how fast it would grow. Your mind wanders to what lies beyond the observable edge. The light from there will never reach you, not because it's too faint, but because space between you and it is expanding faster than light itself can travel. You wave anyway, a small gesture of cosmic optimism. Here, in this colossal silence, you start to feel time differently. It's syrupy, slow. Billions of years unfold like lazy afternoons. Stars flare, die, and recycle themselves into nebulae, and all the while the scale of the universe keeps shifting underfoot. Somewhere, ancient starlight whispers a secret. Expansion isn't uniform. It's patchy, delicate, responsive to invisible forces you can't touch. One of them is gravity, steady, predictable, a clingy friend who never lets go. The other is dark energy, a mysterious, repulsive something that dominates the scene yet never shows its face. It's the reason you're watching everything drift away faster than ever. About 68% of the universe's total energy budget is in that category, unseen, untested, and unnervingly powerful. Matter, the stuff of planets, people, and pizza, barely makes up 5%. The rest? Dark matter. Another invisible crowd doing the heavy lifting of structure. You're the garnish on an overwhelmingly invisible meal. A strange comfort lingers in knowing that you exist in the in-between, between the gravity that binds and the dark energy that divides. Right now, the balance feels precarious but stable, like standing on a frozen lake that's expanding underneath you while cracking at the edges. You can't see the cracks, but you can hear them faintly, echoing through the cold. You start to wonder, what if this expansion were a phase? What if it's not infinite, but something that ebbs like a tide? The thought feels oddly human, to assume even the universe might tire eventually. Some fringe theorist once claimed dark energy could be decaying, its influence thinning as the universe grows. Mainstream science keeps the champagne corked on that one, but the whispers persist. You file it away for later. For now, you drift onward, watching galaxies become mere smudges on a vast stretching canvas. Your eyes adjust to the faint afterglow of the cosmic microwave background, that soft radiation left over from the Big Bang, like the dying embers of a fire that started everything. Its temperature, just 2.7 Kelvin above absolute zero. You could call it chilly, the universe would call it cozy. And there, wrapped in that frozen glow, you realize something profound. Everything you see, every glimmer, every swirl of stars, is the universe mid-breath. It's inhaling, stretching its ribs wide, and one day, that breath might slow. For now, though, you're caught in the motion, part of an expansion older than time itself. You close your eyes, not that it makes a difference out here, and listen. Space hums faintly. It's not music exactly, but something deeper, a kind of low cosmic exhale. You're floating in a universe that refuses to sit still, and the story is only just beginning. You blink and suddenly you're rewinding, like someone hit the cosmic reverse button and all those galaxies start drifting back toward their younger selves. Their redshifted light becomes bluer, brighter, closer. You're heading for the late 20th century, a time when humans still thought the universe's expansion might be slowing down. After all, gravity is clingy by nature. The Big Bang flung everything outward, sure, but shouldn't all that matter eventually tug things back? Maybe the universe would coast to a stop, maybe even reverse. That was the reasonable assumption, until 1998 decided to ruin everyone's tidy equations. It starts innocently enough. A group of astronomers, two actually, decide to measure the distances to faraway type Ia supernovae, those exploding stars that flare with such consistent brightness, they're basically the universe's standard candles. Measure how bright they look, and you know how far they are. Measure their redshift, and you know how fast they're moving away. Simple. The math had worked fine for decades, except this time the data didn't behave. The supernovae were too dim. Not just a little dimmer, but dim enough to mean they were farther away than they should have been. Farther, given the expected expansion rate. It was as if the universe had been quietly pressing the accelerator pedal when no one was looking. One astronomer reportedly muttered, "This can't be right." Others, being scientists, muttered something less polite. But it was right. The universe wasn't slowing down, it was speeding up. You hover beside one of those distant stellar ghosts, watching it flare like a dying eye in the night. Its light began travelling toward Earth when early mammals were still trying to figure out fire. Now, that light whispers the shocking truth of cosmic acceleration. Imagine realizing the cosmos is not only expanding, but accelerating, as though the fabric of space itself has a hidden energy, a push that keeps getting stronger. History marks 1998 as the year dark energy entered the conversation, though the idea had been simmering since Einstein's time. Still, that discovery, confirmed independently by both the Supernova Cosmology Project and the High Z Supernova Search Team, was the moment humanity's cosmic worldview changed. In 2011, the team's leaders shared the Nobel Prize in Physics for the revelation. Historians still argue whether the discovery was inevitable given earlier hints, or whether it truly blindsided cosmology like an uninvited guest at the universe's dinner party. You drift over their data plots, the little dots of observation stubbornly defying the flat line of expectations. There's a strange beauty in the mismatch, the way the universe shrugs at human assumptions. Somewhere a graduate student probably lost a weekend rechecking the calibration, convinced the telescope was lying. But the pattern held. The universe really was racing apart faster and faster. And so, dark energy became the label for our ignorance, a placeholder for whatever unseen force drives that acceleration. You can't see it, you can't bottle it. But its fingerprints are smeared across the cosmos. To explain the expansion, scientists calculated how much of this invisible pressure the universe would need, and it turned out to be about 2/3 of everything. You, your cat, every planet, every atom, all of it is a minority report in a universe dominated by something no one understands. You drift past the Milky Way, outward to the Virgo supercluster, then beyond to the cosmic web itself, the scaffolding of the observable universe. Each glowing filament of galaxies looks like frozen lightning stretching across unimaginable voids. And those voids, they're growing. The galaxies in each filament are held together by gravity, but the filaments themselves are being pulled apart. You're watching the cosmic architecture slowly loosen its joints. A quick historical side note slips in. Long before the 1990s, astronomers had already suspected the universe might be accelerating, though few dared say so aloud. As early as the 1970s, some data hinted at missing mass and unexpected expansion rates. But without precise supernova measurements, it was just speculation. Even Hubble himself, decades earlier, couldn't have imagined that his namesake constant would someday vary. Not because his math was wrong, but because the universe had new plans. One quirky tidbit from those early debates still makes cosmologists chuckle. At one point, estimates of the universe's age were younger than the oldest stars. Imagine telling an ancient red giant, "Sorry, you shouldn't exist yet." That paradox alone hinted that something, maybe expansion itself, wasn't following the rules. Now, from your serene cosmic perch, you see it all aligning. The accelerated expansion, the dimmed supernovae, the deep hum of the cosmic microwave background confirming the same story. The universe is not coasting, it's sprinting. You can almost feel the shift in humanity's cosmic mood. Before, people imagined a universe slowing gracefully, gravity winning in the end, a gentle closure. Now, the story bends towards something far stranger, an ever-speeding void. Galaxies will drift beyond one another's reach. In trillions of years, their light won't even cross the gulf between them. A lonely future awaits, not with a bang or a crunch, but with a quiet vanishing act. But for now, you're still here, floating among the evidence, admiring how elegantly chaos writes its equations. Scientists called it the most important discovery in cosmology since the cosmic microwave background. You might call it a plot twist. As you drift onward, you pass the echoes of press conferences, Nobel citations, headlines blaring, universe expanding faster than expected. You picture Einstein rolling his eyes somewhere in theoretical heaven, muttering about that old cosmological constant of his. And maybe, just maybe, you sense that the story isn't finished. If dark energy can make the universe accelerate, what happens if it changes its mind? For the moment, though, you let the wonder settle in. The stars fade and you're left with a thought both thrilling and humbling. The cosmos is more alive, more dynamic, more unpredictable than anyone ever dared to dream. And as you drift toward the edge of this revelation, you can almost hear the next question forming in the darkness. What, exactly, is this dark energy anyway? You float in that question for a while. What is dark energy, really? The term rolls off the tongue like a mystery novel title, but it's mostly just physics' polite way of saying, we have no idea what's going on. You're suspended in the deep vacuum between galaxy clusters, a realm that looks perfectly empty yet feels anything but. The more you stare into it, the more the nothing seems to shimmer, restless. Quantum mechanics insist this nothing is actually everything, a restless sea of energy bubbling beneath existence. Maybe dark energy lives there, hidden in plain sight. You picture the vacuum not as a void, but as a frothing quantum ocean. Virtual particles pop in and out of existence faster than you can blink, borrowing energy from nowhere and paying it back just as fast. They're the universe's most chaotic accountants. According to quantum field theory, all those fleeting particles should collectively give space an enormous energy density, enough to blow the universe apart instantly. The math predicts a number that's absurdly high, around 10 to the 120 power times larger than what we actually observe. If the universe followed that math literally, there wouldn't be galaxies, planets, or Netflix, just an instant, infinite blast. So clearly something's off. Maybe the theory's wrong, or maybe the vacuum somehow cancels most of its own energy. Historians still argue whether that mismatch is the worst calculation in the history of science or the most illuminating clue we've ever found. Einstein, once again, lurks in the background. When he first introduced the cosmological constant, his famous fudge factor, he meant it to stop the universe from expanding. Now that same constant might explain why the universe won't stop. Irony loves physics. You glide closer to a region of sparse intergalactic space, where the only light comes from distant quasars. Here, the concept of pressure loses all meaning, yet somehow, there's a negative pressure pushing everything outward. Imagine invisible hands stretching the cosmic fabric from within. Dark energy doesn't behave like matter or radiation. It doesn't clump or cluster. It's smooth, eerily uniform, the same everywhere, like a silent background tension. One quirky historical tidbit bubbles up from memory. In the 1960s, before dark energy had a name, a few physicists speculated that space might contain a zero-point energy. Most dismissed it as philosophical fluff. One even joked that if the vacuum really had energy, my coffee cup would have exploded by now. Well, joke's on the coffee cup. It didn't explode, but the universe did. You drift past a region filled with dark matter halos, the invisible skeletons of galaxies. They pull, gather, form. Dark energy, in contrast, pushes. The two forces are locked in a quiet, eternal arm wrestle. For billions of years after the Big Bang, gravity had the upper hand. It pulled matter together into stars and galaxies, but around 5 billion years ago, give or take a cosmic heartbeat, dark energy took over. Since then, it's been calling the shots. That era switch, by the way, happened roughly when our own sun was born. Coincidence? Probably, but it's a poetic one. You can feel the balance even now, a subtle stretching underneath your metaphoric feet. Space grows not because things move through it, but because there's more of it every second. Imagine standing on a rubber floor that keeps expanding under you while you're trying to dance. Every step slides you farther away. That's your cosmic choreography. Scientists have labeled dark energy's behavior with a tidy equation. W equals pressure divided by density. For most known substances, that ratio falls neatly between 0 and 1. But for dark energy, it's roughly -1, negative pressure. That's the math version of saying, instead of pulling, it pushes. It's like the universe looked at Newton's laws and decided, nah, I'll freelance. Still, there's a lingering question that gnaws at cosmologists. Is W exactly -1, or almost -1? If it's exactly -1, dark energy might truly be the cosmological constant, an unchanging feature of space itself. But if it's even slightly different, then dark energy might evolve over time. It could fade, strengthen, or morph into something new entirely. That tiny numerical difference might decide the universe's ultimate fate. You could say it's the most consequential rounding error in existence. Historians still argue whether we should even call it energy. After all, it doesn't behave like any energy humans can manipulate. Some prefer dark pressure, vacuum tension, or simply the cosmological term. But none of those have quite the same eerie poetry. Dark energy, it remains, the mysterious fuel of the universe's runaway expansion. You drift closer to the faint microwave haze that fills all of space, the afterglow of the Big Bang. That glow tells the story of the universe's early youth, and it carries hints of dark energy's later interference. The pattern of its ripples, tiny temperature fluctuations frozen into the cosmic background, shows how dark energy began influencing the geometry of space long before galaxies ever existed. It's like finding an artist's brushstroke in the primer coat of a canvas. And yet, here's the maddening thing. Dark energy doesn't leave fingerprints the way matter does. You can't catch it bending light through gravitational lensing, at least not directly. You can only infer its presence from what doesn't happen. From galaxies not slowing down, from clusters drifting farther apart than expected. Dark energy is a ghost detective's dream. All clues, no culprit. As you hover there, surrounded by infinite quiet, you feel that duality, the cosmos' grand reveal hidden inside its emptiness. Nothingness isn't empty. Space isn't passive. Every cubic meter of the universe hums with invisible tension. and that hum, for now, holds everything together by gently pushing it apart. You tilt your head, if you had one here, and squint into the abyss. Somewhere out there, someone's building a new theory, scribbling equations on a whiteboard, muttering about scalar fields, quintessence, or vacuum decay. Somewhere else, another scientist rolls their eyes and says, or maybe it's just a constant. Chill. The debate hums across centuries, echoing Einstein's own exasperated sigh. For now, you float in the middle of that uncertainty, marveling that the universe's biggest force might simply be the energy of nothing, the same nothing that fills the space between stars, atoms, and even the thoughts flickering through your brain. Nothing is busier than it looks, and just as you start to get comfortable with that idea, a new question surfaces. Softly, inevitably. If this vacuum energy is real, could it ever change? Could the invisible fabric that holds the cosmos together loosen its grip? You drift deeper into the silence between galaxies, following that question like a thread through the dark. Could the vacuum itself change? The airless void hums beneath your awareness, faint and steady, as though the universe is holding its breath. Somewhere, faint equations pulse in the back of your mind, Einstein's field equations stitched into the fabric of reality. They murmur about curvature, mass, energy, and that enigmatic little Greek letter, lambda, the cosmological constant. Einstein added it reluctantly, almost out of embarrassment. In 1917, before anyone realized the universe was expanding, he used lambda to counteract gravity's inward pull, keeping the cosmos static. Without it, his equations predicted either collapse or expansion, both unthinkable at the time. He wanted balance, not movement. Later, when Hubble's 1929 discovery proved that galaxies were flying apart, Einstein reportedly called lambda his biggest blunder. Historians still argue whether he actually uttered that phrase, or if it was apocryphal gossip, but it fits the narrative too well to die. Irony once again adores cosmology. Now, you float beside that constant, that symbol, imagining it not as a number, but as a personality. Calm, patient, stubbornly unchanging. A cosmological constant means that dark energy is just part of space itself, a fixed property of the vacuum. It doesn't evolve, doesn't fade, doesn't care what the universe is doing. It's the same now as it was when atoms first formed, and will be the same when the last photon fades. But then again, humans can't resist poking at constants. What if, theorists ask, it isn't constant? That's where the intrigue begins. You float past a cluster of stars being shredded by a black hole. The light bends, curves, dances in slow arcs around the darkness. You think about quantum fluctuations, the jitter of energy that refuses to vanish even in a perfect vacuum. If those fluctuations create dark energy, then the density of that energy should depend on the quantum fields involved. But the observed value of dark energy is tiny, absurdly tiny. Why doesn't the vacuum tear itself apart under the strain of all those fields? Physicists call this the cosmological constant problem, though calling it a problem is like calling a supernova a flashlight issue. The difference between theory and observation is so colossal, 1 to the power of 120 times, that it's been nicknamed the worst theoretical prediction in physics. Imagine expecting to pay $10 for a pizza and being charged $1 billion trillion instead. You'd either rethink your math or never order again. Historians still debate how to interpret that mismatch. Some argue it's evidence that our understanding of vacuum energy is wrong at a fundamental level. Others think the number might make sense if multiple universes exist, each with different vacuum energies, an infinite lottery of cosmologies, and we just happen to live in the one mild enough to allow galaxies and life. The anthropic principle, they call it. If the vacuum energy were much stronger, no stars would form and we wouldn't be here to complain about it. You drift onward, pondering whether constants can evolve. Maybe dark energy is like a field that slowly shifts over time, a field with potential energy that gradually rolls downhill, like a marble on a shallow slope. If the marble ever reaches the bottom, the universe's acceleration might stop, or, if the slope steepens, acceleration might increase. Theories like this, known as quintessence, treat dark energy as something dynamic rather than static. One quirky tidbit comes to mind. Back in the early 2000s, cosmologists jokingly nicknamed such models rolling scalar fields, which sounds like an indie rock band from a very nerdy dimension. But the idea stuck. It allows for a universe that breathes, a cosmic pulse that could, one day, slow. You pass through a simulation of the cosmic web, the threads glowing like fireflies trapped in honey. The regions between filaments look empty, but it's here that dark energy flexes its power most. You can almost see it as a faint shimmer, a repulsive whisper spreading evenly through every cubic centimetre. The more the universe expands, the more of this nothing exists, and therefore, the more dark energy there is. It's self-feeding, a feedback loop of emptiness. And yet, you can't help but feel that this can't go on forever. Nature usually abhors infinities. Maybe, over incomprehensible timescales, dark energy will leak away, like air escaping an ancient balloon. Maybe the constant isn't constant after all, it's just incredibly slow to change. If so, what would happen to a cosmos built on a fading foundation? You imagine that future. Galaxies slow their retreat. Expansion softens. Space, once eager to stretch, grows tired. The invisible tension loosens its grip, and gravity, quietly patient for billions of years, starts to take over again. Maybe galaxies begin to creep back together. Maybe the great expansion that began 13.8 billion years ago eventually reverses, drawing everything inward once more. A cosmic sigh after a long exhale. The thought is oddly soothing. Everything that drifts apart could someday reunite. But then again, physicists can't agree on whether such a reversal is even possible. If dark energy truly is a cosmological constant, it won't fade. It will keep accelerating the universe until every star, every atom, every molecule is too far from its neighbour to ever interact again. A heat death, a universe that expands forever into silence. You linger at that fork in the road, the two cosmic futures laid out before you. One path leads to eternal isolation, the other to a final collapse. Both, strangely, feel poetic. Both are shaped by the tiniest of details, the sign of a constant, the slope of a field, the way vacuum energy hums through nothingness. Somewhere, a scientist once said, "We call it dark energy because we're still in the dark." And you can't help but laugh softly at that. The universe is both absurd and elegant, an artist that paints in equations and contradictions. You glance back toward Earth, that fragile blue dot still tucked inside its expanding bubble of space. To the people below, this mystery feels remote, abstract. But here, adrift among the galaxies, you sense it intimately. The universe isn't static. It's a living equation, and dark energy is its heartbeat. Whether that pulse slows, stops, or changes rhythm, someday remains the greatest suspense story of all. You've been floating for what feels like forever, but time out here doesn't obey your wristwatch. Seconds and eons blur together as the stars whisper their patient secrets. The hum of the vacuum continues, steady, almost comforting, and you realize you've been hearing the rhythm of an equation this whole time. It's subtle, mathematical music, the song of W, that strange ratio between pressure and density. Somewhere in that number lies the difference between a universe that coasts forever and one that rips itself apart. If you could grab space by the lapels and demand an explanation, W is what it would mumble back at you. For most familiar stuff, say radiation or matter, pressure is positive. Photons, for instance, have a pressure-to-density ratio of about 1/3. They push outward. Cold matter, like dust or planets, or that leftover pizza in your fridge, has practically no pressure at all. W approximately 0. But dark energy? Dark energy plays by different rules. Its W is negative. Roughly -1, give or take a rounding error with apocalyptic consequences. That minus sign flips the whole game. Negative pressure doesn't pull, it repels. It's as if the universe installed a cosmic airbag that keeps inflating with no intention of stopping. If W equals exactly -1, then dark energy behaves as the classic cosmological constant, a steady, unchanging force. But if it's even slightly less than that, say -1.1, then we enter phantom energy territory, a place where expansion doesn't just continue, it accelerates exponentially. Historians still argue whether phantom is a serious term or a physicist's inside joke that got way out of hand. You can almost picture the universe in therapy. Gravity sits on one couch, dark energy on the other, and the counselor, Einstein's equations, tries to keep them from overreacting. Gravity, the counselor says, You pull too much. Dark energy, it sighs. You're pushing back. And there in the middle sits matter, caught in the tension, unsure whether to hold hands or drift away. Back in the early 2000s, when new telescopes began measuring this mysterious W more precisely, the results came in close to -1, but not exactly. The difference was tiny, too small to claim, but it opened an irresistible door. Could dark energy evolve? Could we drift over time, nudging the cosmic expansion toward a new fate? One fringe model even proposed that W might cross -1, switching from a steady push to a destructive yank, a scenario dubbed the Big Rip. You float above a spiral galaxy, its arms twinkling like a slow-motion pinwheel. It looks peaceful, but you imagine what a true Big Rip would feel like from inside. The expansion keeps accelerating until the space between galaxies expands faster than gravity can hold them together. Then the galaxies themselves dissolve, their stars flung apart, planets unbind from suns, atoms from each other, eventually even protons pulled apart as space itself stretches faster than light. It's the universe's version of over-caffeination. Too much energy, too much enthusiasm, everything falling apart from sheer eagerness. Scientists don't panic about this scenario, at least not out loud. Current data suggests W is close enough to -1 that such a catastrophic future would take trillions upon trillions of years, long after the last star has burned out. Still, it's one of those ideas that keeps theorists awake at 3 a.m, staring at their ceiling and muttering, maybe -1.01? There's another calmer possibility. W might be slightly greater than -1, maybe -0.9 or -0.95. That would mean dark energy's influence weakens over time, a fading pressure, not an eternal one. In that case, expansion could slow, plateau, even reverse someday. The universe would take a deep breath in, then gently exhale back toward a denser, warmer state. Some cosmologists quietly root for this scenario. It's tidier, symmetrical. It would make the universe feel like a living cycle rather than an ever-expanding graveyard. But for now, you drift in the uncertainty zone. Observations from satellites like Planck and WMAP, along with galaxy surveys such as DSI and Euclid, keep refining the numbers. Each new decimal place brings hope and fresh confusion. One study nudges W a hair above -1, another nudges it below. The universe, as always, refuses to commit. There's a historical irony in all this. Centuries ago, philosophers debated whether the heavens could change at all. Aristotle thought the cosmos was immutable, perfect, forever spinning in harmony. Then came Copernicus, Galileo, and Hubble, each proving that change wasn't just possible, it was the rule. Now dark energy drags that conversation to its cosmic extreme. Even the vacuum might evolve. Nothing is permanent, not even nothing. You glide near the faint haze of a galaxy cluster, the airless depths between its members lit by X-rays from superheated gas. Gravity tries its best to keep the cluster bound, but dark energy is already at work stretching the space around it. The tension between the two is delicate, like a cosmic tug-of-war where neither side can see the rope. Every atom, every photon, every law of motion depends on who wins. Somewhere, in a chalk-dusted lecture hall, a cosmologist scribbles ρ plus 3p less than 0 across a board. The condition for acceleration. You could almost hear the universe chuckle at the elegance of it. A single inequality describes everything that's ever drifted away. And yet, that same elegance hides the deeper absurdity. No one knows why that inequality holds. A quirky tidbit emerges from your drifting thoughts. Back in the early 20th century, long before dark energy was confirmed, a few scientists proposed a tired light theory, the idea that photons simply lose energy as they travel, making distant galaxies appear redshifted. It sounded neat but crumbled under scrutiny. Ironically, a century later, the universe really is tired, only in the opposite sense. It's running on an invisible overdrive that never quits. As you watch the endless stretching, you feel a strange empathy for those early theorists. They stared into the same darkness and tried to make sense of the same silence. Now, even with precision satellites and quantum field equations, you're still chasing a whisper. Maybe that's the real beauty. The universe keeps just enough mystery to make curiosity worth the effort. The stars blur again, your cosmic motions speeding subtly as expansion carries you farther into the deep. You think about that equation of state, W, still humming somewhere beneath reality's skin. It's more than a number. It's a promise. Whatever value it truly holds will decide the universe's final act: collapse, chill, or rip. For now, though, everything continues, steady, calm, expanding. The vacuum hums its negative tune, galaxies dance in slow retreat, and you, tiny stowaway of starlight, float onward with the rhythm. Somewhere, the universe keeps its secret, and somewhere, far ahead, the next clue is waiting in the data, the subtle fingerprints of a force that refuses to explain itself. You keep drifting, and the light grows thin. The galaxies that once burned bright are faint now, like old memories dissolving at the edges. Out here, expansion has stretched everything, light, distance, and patience to their limits. You're following the cosmic detectives now, the ones who dared to measure that stretching and give it a name. They're huddled in observatories, satellites, and high-altitude balloons, chasing whispers of the universe's acceleration across wavelengths invisible to the naked eye. If dark energy is the invisible hand behind it all, then these scientists are its ghost hunters. You hover beside them as they sift through data, every pixel a clue. They call it cosmology's great survey, but really it's a treasure hunt written in starlight and noise. Your first stop is a mountaintop observatory in Chile. The Atacama air is thin, the sky almost violent in its clarity. Below, the desert stretches like the surface of Mars. Inside the dome, an array of mirrors tilts toward the heavens, tracking a supernova-like curve. Each spike and dip is a cosmic timestamp, a record of how fast the universe was expanding when that star died. You watch the data appear on a screen, bright dots on a graph that collectively map the universe's heartbeat. The slope of that curve tells astronomers how the cosmos has stretched over billions of years. A researcher murmurs something about standard candles, and you smile, remembering those Type Ia supernovae from before, the old faithfuls of cosmic distance measuring. They're still the workhorses, still flashing their calibrated brilliance from galaxies too far to imagine. Each explosion adds another bead to the rosary of expansion, but supernovae aren't the only witnesses. Next come the BAO, or baryon acoustic oscillations, subtle ripples left over from the primordial plasma of the early universe. Think of them as sound waves frozen into space, a faint cosmic drumbeat that shaped how galaxies spread apart. You glide through one of those frozen ripples now, a region where galaxies are slightly more likely to appear, spaced about 500 million light-years apart. Astronomers measure that regular spacing like tree rings, tracing how those rings have widened with time. Historians still argue whether BAO were first recognized as a standard ruler, or whether someone just noticed the pattern by accident. Either way, those ripples now serve as the universe's measuring tape, confirming, again, that space keeps stretching faster than gravity can reel it in. Next, you drift toward orbit, where the Planck satellite hums quietly, its instruments tuned to the cosmic microwave background. The oldest light there is, 13.8 billion years in the making. You glide through that ancient radiation, its warmth a ghostly 2.7 Kelvin. The light is mottled with faint temperature spots, tiny variations only millionths of a degree apart. Those spots encode everything: how dense the early universe was, how fast it expanded, how much dark energy it carries today. The data stream flickers past you like static snow, elegant chaos. Each pixel of that background tells a story about geometry. Too much dark energy, and the universe's fabric would curve outward like the inside of a balloon. Too little, and it would curl inward like a saddle. What Planck saw was eerily flat, balanced on the edge between the two, but with just enough extra push to suggest a subtle, persistent expansion. The numbers fit perfectly with a universe dominated by dark energy. One quirky detail makes you grin. The Planck spacecraft is powered by plutonium-238, the same isotope that once fueled the Voyager probes. Somewhere, two ancient spacecraft are drifting beyond the heliosphere, still whispering telemetry to a planet that invented dark energy decades after they launched. The universe has a sense of timing. You move next to the Sloan Digital Sky Survey, thousands of telescopes mapping millions of galaxies. The resulting map looks like cosmic coral, clusters, filaments, voids, all woven through with the faint thread of expansion. Each galaxy's redshift acts like a speedometer reading, each distance measurement another breadcrumb in the grand chase. Astronomers squint at those plots, trying to spot the fingerprints of fading energy. They compare nearby galaxies to ancient ones, looking for signs that the acceleration rate is changing. The work is meticulous, obsessive. Cosmic detectives don't get car chases, they get scatter plots. Historians still argue whether these measurements will ever give a clear answer. Some insist dark energy must eventually reveal a pattern, perhaps a slow decline in strength. Others believe it's truly constant, the eternal hum of the vacuum. Still others whisper fringe ideas that the acceleration might be a mirage caused by space-time curvature on large scales, or by something even stranger, extra dimensions bleeding gravity's influence into our own. You watch the arguments flicker across conference slides, equations battling like duelists. Someone mentions a quintessence potential, another counters with modified gravity. There's polite laughter, and then more coffee. Science is patient theatre. Outside those conference halls, the real data keep flowing. Gravitational lensing surveys twist light into arcs and rings, letting astronomers map how mass, and maybe dark energy, distorts space itself. The Euclid mission, sleek and silver, is out there right now. Well, in your imagined now. Scanning billions of galaxies to catch the faintest hint of a shift in WW, that mischievous ratio from before. And all this effort, decades, billions of dollars, sleepless nights, is driven by one suspicion, that dark energy might not be constant, that maybe, just maybe, the universe is whispering a change, a soft decline in its outward push. You linger for a moment, watching photons arrive at a telescope mirror after a 10 billion year journey. The astronomer logs the measurement, unaware that light left its source when Earth's continents were still in different places. You imagine the light itself sighing in relief, finally made it. A gentle joke surfaces in your mind. One cosmologists like to tell themselves, "We're mapping the universe's expansion, but by the time we finish, it will have doubled in size again." You chuckle softly. Out here, jokes age well. The silence that follows is comforting. You realize that in the grand investigation, humans are still beginners, their instruments fragile, their theories provisional, but there's beauty in that humility. The cosmos keeps its secrets for a reason. It wants you to keep asking. You watch as the observatories power down for the night, their domes closing like mechanical eyelids. The stars outside stay bright, patient, waiting for the next generation of curious eyes. Somewhere, between the noise and the void, a faint pattern stirs. Something in the data hinting that maybe, just maybe, dark energy's steady song is beginning to falter. You can't prove it. No one can. But you can feel it, faint as a heartbeat beneath the static, a universe that might be changing its mind. You drift with that suspicion. Dark energy fading, letting it settle in your thoughts like cosmic dust. It's an idea that feels both dangerous and irresistible. For years, cosmologists treated dark energy as constant, a polite background hum that just happened to dominate the universe. But lately the numbers have begun to twitch. The light from ancient supernovae doesn't line up perfectly with expectations. Some data suggest the acceleration rate might have been slightly stronger in the past than it is now. A whisper in the vacuum. Maybe the great cosmic push is slowing. If dark energy really is fading, then everything changes. The neat symmetry of the lambda CDM model, the lambda cold dark matter standard, starts to wobble. You can almost hear cosmologists groaning as decades of tidy fits begin to unravel. You hover over a virtual whiteboard scrawled with formulas, omega lambda t instead of a fixed omega lambda, a time-dependent constant, a contradiction in terms that scientists can't stop scribbling anyway. Historians still argue whether the first hints of fading dark energy came from observation or imagination. In the early 2000s, a few bold researchers published models suggesting that the dark energy density could evolve over time, tied to the scalar fields of the early universe. Most of their peers smiled politely and called it interesting but speculative. Then came more data, tighter supernova curves, refined BAO maps, subtle lensing effects, and suddenly the speculation didn't look so lonely. You glide closer to a visualization of the data. Two smooth lines, nearly identical but not quite. One represents constant dark energy, the other a slightly declining form. The gap between them widens just enough to raise eyebrows. It's not proof, but it's the kind of almost proof that drives theorists to pour another coffee and stay up until dawn. They've given it names: dynamical dark energy, thawing quintessence, decaying vacuum. Each one suggests a story of energy fields that evolve, or of space itself slowly relaxing after cosmic inflation. Imagine the universe as a shaken soda can, its fizz gradually going flat. The pressure that once inflated space might now be leaking away, molecule by molecule, if molecules existed in the vacuum. You pass through a region of the simulation where the dark energy density has been scaled down by a fraction of a percent. The effect is subtle but profound. Galaxies drift apart a little more slowly. The cosmic web begins to hold together longer. It's almost like watching the universe catch its breath. One quirky anecdote bubbles up. During a 2019 cosmology conference, a researcher compared the fading energy hypothesis to cosmic decaf. The universe, they joked, might be losing its caffeine, still expanding but less frantically. The laughter in the room was tired but hopeful. Cosmologists love metaphors almost as much as they love uncertainty. The fading theory also dovetails with one of physics' oldest superstitions: nothing lasts forever. Even the vacuum, that most stable of entities, might be temporary. Some models of quantum field theory suggest that our universe could exist in a false vacuum, a metastable state that could eventually decay into something with a lower energy. If that ever happens, space itself would suddenly reconfigure, expanding at light speed in a bubble of new physics that erases everything it touches. You probably wouldn't notice. It would be over too fast for awareness. Comforting, right? But fading dark energy doesn't have to mean catastrophic vacuum decay. It could simply mean the pressure that drives expansion is running out of fuel. The scalar field behind it could be flattening, its potential energy relaxing towards zero. The universe might be winding down not with an explosion, but with a sigh. Historians still debate how to interpret the hints in the data. Are we really seeing change, or just statistical noise amplified by wishful thinking? Cosmic variance is a tricky thing. You can only observe one universe, one history, one set of expansion rates. Maybe we just live in a slightly under-dense region of space, skewing the numbers. Or maybe, as some suggest, there's an unknown systematic error, a calibration flaw in the telescopes, or dust that subtly dims the supernovae. Science, after all, is allergic to certainty. You float above a mock-up of the Euclid mission's results, its deep-field galaxies stretching across your vision like glitter spilled on velvet. The data show a pattern, faint signs of less acceleration in the recent epoch than in earlier times. It's within the margin of error, but barely. The universe might be whispering that its push is softening. What would that mean for everything? You picture it. Billions of years from now, expansion slowing like a car coasting uphill. Galaxies that once sped apart begin to linger in view. Gravity, patient as ever, starts to tug more effectively. Structures hold together longer. The cosmic microwave background continues to cool, but more gently as the rate of expansion eases. Stars still die, but the void between them grows more slowly. The cosmos itself seems to take a long, deep breath. There's a comforting symmetry to it. For decades, cosmology's story has been one of runaway acceleration, a universe doomed to isolation and cold. But fading dark energy paints a different picture, one where balance might be restored, where expansion and attraction eventually meet halfway, maybe even where new cycles could begin. Of course, not everyone's on board. Some scientists argue that fading dark energy is just the universe's version of static, a statistical fluke amplified by the human craving for narrative. They point to the consistency of the lambda CDM model, the precision of the CMB fit, the elegance of simplicity. Don't fix what isn't broken, they say. The cosmological constant works. But still, the whisper persists. The newest redshift surveys, the gravitational lensing maps, the patterns in galaxy clustering, they all leave a little wiggle room, a faint tantalizing slope downward in the data. Maybe dark energy really is decaying. Maybe the universe is aging out of its hyperactive phase. You float in that possibility, feeling both awe and melancholy. If dark energy fades, then one day the expansion will slow, perhaps even stop. But if it never fades, if it stays constant, then everything will keep drifting apart forever, until even light becomes too lonely to find a friend. Between those two fates lies a cosmic pause button, a chance for the universe to rest. And as you drift there, halfway between gravity and the void, you realize something. This isn't just physics, it's a meditation on impermanence. Everything, stars, galaxies, even the vacuum, might one day fade. Maybe that's not tragic at all. Maybe it's just how eternity breathes. You hang there in the dark, feeling that faint tremor in the cosmos, the suggestion that the great push might be easing. It's a strange feeling, watching eternity start to slow. At first, you barely notice. The galaxies still drift apart, redshifts still stretch their wavelengths, but somewhere deep in the background arithmetic, the numbers are softening. If dark energy really is fading, then gravity, that quiet and patient sculptor, begins to stir again. You imagine the universe as a grand race between two invisible hands. One pushes outward, the other pulls inward. For billions of years, gravity did the pulling, forming stars, galaxies, clusters, everything you can name. Then, about 5 billion years ago, dark energy seized the wheel and hit the gas. The expansion sped up, galaxies began to lose touch, and the universe started its long escape from itself. But what happens when that cosmic fuel tank starts to run low? The first sign would be subtle, the rate of acceleration decreasing. Galaxies wouldn't stop moving away, but their outward drift would slow. Like a car coasting up a gentle hill, they'd still have momentum, but you'd start to feel the slope fighting back. The space between clusters would still grow, but the growth would taper, millimeter by cosmic millimeter. You wouldn't see it in your lifetime, or in 1,000, but the math would know. Historians still argue whether this tug-of-war is best described as a battle or a balance. Some ancient philosophies believed the universe always cycled between creation and collapse. Hindu cosmology, for instance, spoke of kalpas, vast epochs of expansion followed by contraction, endless breaths of Brahma. Modern physics, with its equations and constants, may sound less poetic, but it circles the same idea. What goes out may one day come back. You drift into a simulation where the universe's expansion begins to slow. The cosmic web tightens just slightly. Voids stop ballooning so fast. Galaxies that were once destined for eternal separation remain faintly visible to one another. In this gentler universe, cosmic loneliness takes longer to set in. The night sky of the distant future would hold more light than in the constant lambda scenario. A mercy of fading. You float near a massive galaxy cluster, Perseus maybe, and watch its gravitational tendrils hold fast to its galaxies. Dark energy's weakening grip allows gravity to deepen its hold. Stars cluster tighter, collisions between galaxies become more common. Somewhere in a spiral arm, a star-forming region flares bright as newborn suns ignite. It's as if the universe, slowing down, has found the time to gather itself again. A quirky historical note surfaces. In the mid-20th century, long before dark energy's discovery, cosmologists debated whether the universe's expansion might eventually stop and reverse. They called it the Big Crunch scenario. The idea fell out of favour once acceleration was confirmed, but fading dark energy has quietly revived it, not in its old fiery finality, but as a possibility reborn in moderation. Maybe not a crunch, but a cosmic break tap. The beauty of it lies in the middle ground. The universe doesn't have to end in fire or ice. It could simply slow to a graceful coast. Expansion might approach zero asymptotically, never quite stopping but never racing away either. A universe in quiet equilibrium. Cosmologists call this coasting cosmology, though you can almost hear the poetry beneath the term, a cosmos content to drift. You glance back at the Milky Way, that familiar spiral island in an infinite sea. Right now, its local neighbourhood, the local group, is bound together by gravity, dark energy or not. Our galaxy, Andromeda, and a few dozen smaller ones are already locked in their slow-motion merger, due to collide in about 4 billion years. Fading dark energy wouldn't change that meeting, but if its weakening continued, then maybe future galaxies, billions of light years away, would also find themselves drawn back together. The cosmic diaspora could, eventually, begin to reverse. Still, not everyone buys the idea. Some physicists argue that a fading cosmological constant violates the simplest reading of general relativity. Constants should stay constant, they insist. But others counter that even Einstein's equations leave room for change if the underlying field evolves. The debate is lively, heated, and often philosophical. Does the universe obey simplicity or surprise? Historians will one day argue whether we were witnessing the first cracks in our simplest model, or just our desire to see patterns in noise. You picture the universe's far future if dark energy fades steadily over trillions of years. Gravity would slowly regain dominance. Galaxy clusters might stop drifting apart. The cosmic web, stretched thin by eons of expansion, could thicken again. Somewhere, faint starlight from ancient galaxies could once more cross the gulf and be seen by new observers. Perhaps future astronomers, if any remain, will look into their telescopes and notice the opposite of what we see, the universe getting denser, warmer, brighter. But here's the twist. If dark energy fades too slowly, that reversal might take longer than any star can last. The cosmos could enter a long twilight where acceleration wanes but never quite ends. Expansion slows but never stops, leaving a liminal state of near stillness. A universe neither flying apart nor falling together. It's hard not to feel the poetry in that. Eternity balanced on a knife's edge of motion. You watch that balance play out in your imagination. The galaxy's outward dance slows, the music softens, and you realize you're witnessing the closest thing the cosmos has to aging gracefully. No explosions, no rips, no collapses, just the quiet easing of tension after a long exertion. It's almost peaceful. Somewhere, a cosmic background photon slides past you, its wavelength stretched to near infinity. It's cold, ancient, weary. You follow it, tracing its path through the vast emptiness. If dark energy fades, this photon will travel forever. Not because space stretches it endlessly, but because space itself stops changing beneath it. It will drift through a stable, unhurried cosmos, a relic of the wild youth that once was. You realize then that if the push weakens, the universe doesn't lose its wonder. It gains texture, history, the slow beauty of transformation. Expansion doesn't have to mean isolation, and stillness doesn't have to mean death. Maybe when the great acceleration ends, the cosmos will finally have time to look back on itself, to remember what it created while it was busy rushing outward. You smile at the thought. The universe that forgets how to hurry might be the kindest universe of all. You float through that quiet, slowing cosmos, letting the thought sink in. If dark energy keeps fading, gravity will eventually have its comeback tour. You can almost feel it gathering strength in the shadows, a force that never went away, only waited. It's like the universe has been holding an invisible tug-of-war for billions of years, and now the team on the pull side starts to inch the rope back. Slowly, imperceptibly, the great expansion begins to resist itself. At first, you wouldn't notice. Galaxies would still drift apart, light would still stretch, but the acceleration would soften, its edges blunting like an old blade. You imagine the universe as a marathon runner who's been sprinting since the Big Bang, 13.8 billion years of relentless momentum, and now, finally, it starts to tire. Each stride covers just a little less distance. If this trend continues long enough, there comes a moment physicists call the turnaround. That's when the outward motion halts completely, when the universe reaches its maximum size before beginning to contract. You could think of it as a cosmic inhale following an impossibly long exhale. Everything slows, then reverses. Expansion becomes implosion. The galaxies that once fled one another begin to drift back together under the pull of their combined gravity. Historians still argue whether Einstein himself ever considered such a reversal seriously. Some say his original equations, even with lambda, allowed for a cyclic cosmos. Others claim he dismissed that idea after Hubble's discovery of expansion. But later cosmologists, especially in the mid-20th century, loved the symmetry of it. The Big Crunch became one of the grand contenders for how the universe might end, a fiery mirror image of the Big Bang. You drift inside a simulation of that future, watching galaxies decelerate. It happens on timescales so vast that even atoms would struggle to remember the difference between before and after, but you can imagine it. First, the expansion stalls, and the cosmic microwave background, the faint afterglow of creation, stops cooling. It hangs there at some final temperature, neither fading nor brightening. Then, as contraction begins, the background slowly warms again. Space itself compresses. The wavelengths of light that had been stretched thin for eons begin to shorten. Red becomes blue. Cold becomes hot. The universe, in a strange sense, starts to rewind. At first, only the largest structures feel it. Superclusters of galaxies, those sprawling webs of matter begin to inch closer. Voids, the vast empty bubbles between them, start to shrink. Over unimaginable ages, gravity's long patience pays off. Galaxies that once said goodbye now head home. Stars collide more often. Cosmic mergers become the rule rather than the exception. You can almost picture the sky filling again, constellations rearranging, new supernova igniting in every direction. There's an eerie familiarity to it. You've seen expansion all your life, but contraction looks like déjà vu in reverse, like watching a movie of the cosmos being slowly rewound. Somewhere, the Milky Way, long since merged with Andromeda into a single swollen elliptical galaxy, starts to feel the gentle nudge of other clusters drawing near. Space shrinks around it. What was once billions of light-years of separation becomes millions, then thousands. A quirky bit of science trivia crosses your mind. The concept of a contracting universe was once so fashionable that a few 1970s physics textbooks described the oscillating universe as the likely fate. They imagined endless cycles of bang, expansion, crunch, repeat, a kind of cosmic heartbeat. Eventually, the Big Bang model's dominance and the discovery of acceleration buried that idea, but fading dark energy could resurrect it. Perhaps the universe has been doing this forever, expanding, collapsing, expanding again, each cycle erasing the memory of the last. Historians still debate whether time itself would reverse in such a scenario. Would entropy, that arrow of disorder, start to decrease as the universe compresses? Most physicists say no. The laws of thermodynamics are stubborn, but it's hard not to wonder. If everything moves backward, what happens to time's meaning? You might wake up in a collapsing cosmos someday and not even realize you're heading home. You watch the imagined collapse accelerate. Once gravity dominates fully, there's no stopping it. Space contracts faster and faster, pulling everything inward. Galaxies collide, stars explode, black holes merge, and the sky brightens with furious energy. Temperatures climb as all that mass and radiation compresses into a smaller and smaller volume. Eventually, the entire universe could shrink into a blazing sphere of heat and density, the mirror of its own birth. It sounds terrifying, but out here, drifting among equations instead of atoms, it feels strangely serene. The symmetry is beautiful. What began as a burst of energy returns to its source, completing the circle. You could almost call it cosmic recycling. Maybe the energy from one universe seeds the next. Maybe the big crunch triggers a new Big Bang, and the cycle begins anew. You let yourself imagine that infinite loop. Each universe slightly different, each set of physical constants tuned a little more finely, each round a new experiment in existence. Civilizations rise and vanish, galaxies bloom and fade, but the rhythm endures. Expansion, contraction, rebirth, like cosmic breathing. The Hindu sages called it pralaya, the dissolution that precedes creation. Modern cosmology calls it cyclic cosmogenesis. Different words, same more. Of course, this is only one possibility. Some theorists argue that a fading dark energy might never allow a full reversal. If it asymptotically approaches zero but never quite crosses it, expansion might slow without ever collapsing. The universe would coast indefinitely, sluggish, stretched, but still outward bound. Others whisper about bounce models, where quantum effects at the smallest scales prevent total collapse, turning the crunch into a gentle rebound instead of a final end. For now, all you can do is float here, watching the future unspool across possibilities. You trace the balance point, the exact moment when expansion halts, when the universe holds still. It's a fleeting instant, and yet, in that stillness, everything feels infinite. The cosmic tug-of-war pauses mid-motion. You sense the silence that must precede either creation or collapse. Maybe, when the push finally ends and the pull begins, the universe won't mourn. Maybe it will simply keep breathing, changing phase, keeping time to a rhythm only eternity can hear. And you, lucky wanderer, get to float at the cusp of it all, between what was and what's about to return. You hover at that still point, the tipping balance between outward stretch and inward pull, and it feels like the universe itself is holding its breath. The galaxies around you, faint pinwheels suspended in ink, seem to wait for the next cue. Which way will it go? From here, does the cosmos freeze, fall, or fly apart? There are three great endings on the table, whispered like bedtime stories for cosmologists: the big chill, the big rip, and the big bounce. You've already met the crunch, the scenario where gravity wins and the universe folds inward. But the cosmos is generous with options. If dark energy doesn't fade, or worse, if it grows stronger, there are stranger fates still to come. You start with the quietest one first. The big chill, sometimes called the heat death, is what happens if dark energy stays constant forever. Expansion continues at a steady acceleration until everything, absolutely everything, is too far apart to talk to anything else. Galaxies become cosmic islands, drifting away beyond each other's horizons. Over trillions of years, stars exhaust their fuel, white dwarfs cool to black, and even black holes evaporate via Hawking radiation. The universe doesn't explode, it just grows dimmer, like a campfire burning down to its last coal. Historians still argue whether heat death is a misleading name. Technically, the universe ends not in heat but in perfect cold, a temperature so low that motion itself becomes meaningless. Every particle drifts alone in silence. Entropy, the measure of disorder, reaches its maximum. There's nothing left to rearrange, no work left to do. It's the end of everything, not with a bang or even a whimper, but with a sigh that stretches across infinity. You drift through that frozen imagination, the stars now only ghosts of photons, their light so redshifted it's more like memory than radiation. Space itself grows endlessly, meaning that even those memories are stretched thin until they vanish. Somewhere you think you can almost hear the universe yawn. Then you shift your gaze toward the more dramatic option, the Big Rip. This one only happens if dark energy strengthens over time, if its negative pressure keeps dipping past -1 on that slippery W scale. In this scenario, acceleration doesn't just continue, it feeds on itself. Every galaxy, every cluster, every atom becomes caught in an ever faster stretch. You can imagine the sequence. First, distant galaxies drift away beyond sight. Then, the Milky Way's own stars lose their gravitational bonds. Then planets, then molecules, and finally, the atomic nuclei themselves get torn apart as the fabric of space-time outruns the very forces that hold matter together. It's the universe's version of pulling a sweater thread until the whole thing unravels. Some physicists have tried to time this apocalypse. If W were, say, -1.2, the rip could happen in roughly 20 billion years. Not tomorrow, not next Tuesday, but uncomfortably soon on cosmic scales. You'd never see it coming. One minute the night sky would look as it always had. The next, every point of light would elongate, dissolve, and then you'd dissolve too. No pain, just unmaking. Comforting, in a morbid sort of way. A quirky story lingers about this scenario. During one conference in the early 2000s, a presenter showed a slide labelled The Big Rip rated R. The audience laughed nervously. Humour helps when the universe is plotting creative forms of annihilation. Still, the Big Rip is an extreme case, and the evidence doesn't seem to support it yet. If anything, the hints of fading dark energy point in the opposite direction, toward less tearing, not more. Which brings you to the third contender, the most hopeful of the bunch, the Big Bounce. This version treats the universe not as a one-time explosion or eternal expansion, but as a cosmic cycle. Expansion slows, stops, reverses, collapses, then rebounds again in a new Big Bang. It's the Phoenix model of cosmology, the universe reinventing itself forever. You drift into that possibility. The contraction you imagined before continues until the cosmos becomes dense and hot again. Quantum effects, those jittery subatomic antics that never fully go away, kick in, preventing total collapse. Instead, space rebounds. The laws of physics reset. The matter of the old universe becomes the fuel of the next. Historians still argue whether ancient thinkers, like the Stoics or the Indian Vedic philosophers, might have predicted something like this long before modern science did. The Stoics believed the cosmos was periodically consumed by fire, only to be reborn anew. Ekpyrosis, they called it. Modern cyclic models, oddly enough, use the same term. The idea never quite dies, it just waits for better math. Quantum cosmology adds its own twists. Maybe each bounce alters the constants of nature slightly, creating a multiverse of evolving universes. Maybe our current one is just the latest in an infinite lineage of expansions and contractions. Or maybe, if dark energy truly fades to zero, this is the last great cycle, a final breath before silence. You drift through these three futures like stations on an infinite train line. The big chill's quiet emptiness, the big rip's violent ending, the big bounce's hopeful renewal. Each depends on the behavior of dark energy, that invisible puppeteer pulling the strings of space. If it stays constant, chill. If it grows stronger, rip. If it fades, bounce. And right now, you're somewhere in between, riding the delicate crest of acceleration, unsure which way the curve bends. The measurements hint at a slight decline, but the error bars still laugh at certainty. It's like trying to predict a trillion-year future based on a few decades of data, humanity's hubris in one elegant plot. Still, you can't help feeling drawn to the poetry of a fading universe that folds itself back up, starting over in a new blaze of creation. It feels like closure, not catastrophe. Like watching a candle go out only to see another ignite from its last spark. Somewhere in the distance you imagine that new beginning, the next universe blooming from the ashes of this one. Maybe its constants will be different. Maybe gravity will be gentler. Maybe dark energy will be a little less fickle. And maybe, just maybe, there'll be someone there, billions of eons hence, floating through the dark, wondering how their own cosmos will end. You smile. Every ending is just a beginning in disguise, and dark energy, whatever it truly is, might be the thread tying them all together. You coast in that uneasy quiet, the afterglow of cosmic endings still drifting around your mind like smoke. The idea of the universe dying or rebirthing has always been a magnet for imagination. You can't help it. Humans have been picturing the end of everything since they learned to look up at the sky. If the stars were the first clocks, then the question of when they stopped ticking was the first bedtime story. Tonight, you get to follow that thread, how people through history have stared into the dark and tried to name the final act. You start far back in the firelight of the ancient world. Around a Mesopotamian hearth, storytellers murmured about floods and cycles, the gods washing the slate clean to start again. In Egypt, the sun god Ra sailed his bark through the underworld each night to be reborn at dawn, a daily rehearsal of cosmic renewal. Farther east, Hindu cosmology laid out entire epochs, yugas, each ending in dissolution and rebirth. The universe didn't just end, it pulsed like a divine heartbeat. The Norse had Ragnarok, that final winter when gods and monsters devour one another and the world sinks beneath the sea, only to rise again, green and empty. The Maya counted down their long cycle calendar to 13 Baktuns, envisioning time itself as a loop. Even the Greeks, those early philosophers who gave us the language of reason, couldn't resist an apocalypse. The Stoics imagined a universe consumed in ekpyrosis, a grand cosmic fire. Historians still argue whether these mythic endings were symbolic or scientific, whether people truly expected the world to die, or just liked the drama of imagining it. Maybe both. Every civilization, it seems, looked up at the stars and saw the same tension. Creation paired with destruction, eternity paired with time. Fast forward to the Middle Ages and the end of the world gets personal. In Europe, theologians folded apocalypse into morality, judgment, revelation, resurrection. Time had a direction now, a divine arrow. The universe wasn't cyclical anymore. It was a story with a beginning, middle, and climactic end. The earth might burn, the heavens might open, but it would mean renewal, not randomness. The cosmos was no longer an infinite breathing thing, it was a plan. And then came science, the heretic child of curiosity, and suddenly, the universe wasn't centered on Earth or humanity at all. Copernicus moved us off stage, Newton gave gravity its lines, and eventually Einstein rewrote the script entirely. The heavens weren't eternal domes anymore, they were elastic, expanding, alive. For a while, physicists believed gravity would pull everything back in, a neat mechanical big crunch. The end was calculable, rational, almost polite. Then came that 1998 revelation, the universe accelerating instead of slowing, and the mood changed again. The apocalypse became colder, quieter, less like divine fire and more like entropy. The new fear wasn't judgment, but emptiness, not a burning sky, but one that fades until nothing is left to see. You imagine how strange that must have felt. Scientists realizing that the cosmos, far from running down toward collapse, was sprinting toward isolation. It was the inverse of every myth, the end of everything, not by destruction but by distance. If dark energy stayed constant, the big chill was inevitable. The last star would die, the last black hole would evaporate, and time itself would become meaningless. And yet, here you are, imagining another plot twist. Maybe dark energy isn't constant. Maybe it's fading, and the universe, instead of freezing, might one day draw itself back together. The mythic pendulum swings again, from heat death to rebirth. The more physics advances, the more its endings sound like old poetry wearing new equations. You drift across centuries of human imagination, from prophets to physicists, from fireside stories to collider data. The language changes, but the tone stays the same: wonder, dread, beauty. Even now, some modern cosmologists indulge in quiet speculation. Maybe the end isn't an end at all. Maybe new universes bud off from black holes, each Big Bang just the other side of a collapse. That's the multiverse idea. Elegant and unprovable, beloved and maddening. In that picture, the universe never really dies. It just molts. A quirky note. The philosopher Friedrich Nietzsche in the 1880s mused about eternal recurrence. The idea that every moment repeats infinitely, every life lived again and again. He meant it metaphorically, but physicists later noticed that cyclic cosmology could make it literal. The cosmos as an eternal remix. If you've ever felt déjà vu, maybe that's space-time winking at you. Historians still argue which version of the end people find more comforting: the fiery collapse, the frozen silence, or the endless loop. Each says something different about what we hope for. The crunch promises reunion, the chill promises peace, the bounce promises renewal. Even the big rip has its strange appeal: a clean slate, absolute release. You let yourself drift among these imagined futures. You picture them painted on cathedral ceilings, carved into temple walls, etched into data graphs. The symbols change, but the awe remains the same, that humans, small as we are, dare to think about the fate of everything. And maybe that's the real constant. Not dark energy, not gravity, but curiosity. Every culture has looked at the stars and asked, what happens when they're gone? The question binds us across time like gravity binds the cosmos. You take one last look at the faint constellations of mythic endings, the flames of Ragnarok, the serpent devouring its tail, the clockwork equations of Einstein. Somewhere in that collage lies the truth, or at least the shape of it. The universe began once and it will end once, or many times. But in between, it tells a story of persistence. For now, dark energy still hums, expansion continues, and humanity keeps building better telescopes to measure its own oblivion. You can almost laugh at the optimism of it, measuring your doom in gigaparsecs per second. But that's the beauty of consciousness in an expanding universe. You don't just live in the story, you get to narrate it. And so, you float onward, past the myths, past the equations, toward the next question shimmering in the dark. If dark energy can fade, could it evolve? You drift again through the faint shimmer of intergalactic space, following that next question like a glint in deep water. If dark energy can fade, maybe it can evolve. The thought has been haunting cosmology for decades now. What if the thing driving the universe's acceleration isn't a fixed property of emptiness at all, but a field, alive in its own slow way, changing texture as the cosmos ages? You've reached the era of quintessence, the theory that turns dark energy from a static background constant into something dynamic, something that breathes. Picture it this way. Instead of an unchanging lambda woven into Einstein's equations, space is suffused with a scalar field, a single value at every point, like temperature or pressure in air, that carries potential energy. Over time, that field can roll down its potential, trading energy for motion, shifting how strongly it pushes on space-time. If it rolls gently, the universe accelerates softly. If it settles, expansion coasts. If it tumbles, the cosmic push might even reverse. It's like giving the vacuum a mood swing. Historians still argue whether the first whisper of this idea came from particle physics or from the philosopher's instinct that nothing truly stays the same. In the late 1990s, when the supernova data first confirmed acceleration, a few theorists were already sketching models with evocative names: tracker fields, freezing models, thawing quintessence. Each told a slightly different story about how dark energy might behave through time. You glide beside one of those mental landscapes, a graph showing the potential of the quintessence field, shaped like a gentle valley. The field is the marble, the valley floor, its destiny. In the early universe, the marble sits high on the slope, its stored energy immense. As cosmic time passes, it slides downward, releasing energy into the fabric of space-time. The steeper the slope, the faster the release, and the more quickly the universe's acceleration changes. It's graceful physics, cosmology told as gravity's long exhale. You hover near a simulation where the field's strength slowly weakens. Galaxies drift apart a little less rapidly. Background radiation cools a little less quickly. The difference seems tiny, fractions of a percent, but across billions of years it reshapes destiny. A fading quintessence could mean the cosmos eventually halts its expansion, or even bounces. A strengthening one could drive it to the Big Rip. The tiniest tilt of that potential decides everything. A quirky historical tidbit floats by. The name quintessence comes straight from Aristotle's fifth element. The ether, the pure substance filling the heavens beyond earth, air, fire, and water. For centuries, people believed stars swam through that invisible medium. Modern physics exorcised the ether, only to resurrect it in mathematical form. The universe, it seems, can't resist nostalgia. Down on Earth, you peek over a researcher's shoulder. She's running Markov chain simulations, comparing cosmological parameters from Planck, DES, and Euclid surveys. Her screen glows with contour plots, lines curling around the magic coordinate W equals -1. A fraction above it means quintessence is freezing, slowing toward constancy. A fraction below means it's thawing, waking up and gathering strength. Every new data point tightens or loosens those loops, science as embroidery. Historians still argue whether quintessence counts as a new force or just a new label for ignorance. Some theorists tie it to ideas from high-energy physics. Perhaps it's a leftover field from inflation, or a cousin of the Higgs. Others treat it more like weather, an emergent phenomenon of space-time itself. And of course, a few skeptics shrug and say, "Show me the measurement first." They have a point. After 25 years of searching, no one has yet caught quintessence in the act. You drift farther from the galaxy planes, where the cosmic background becomes a uniform fog. In this emptiness, the quintessence field, if it exists, would be everywhere at once, smooth and subtle. Imagine it as a faint pressure you can't feel but that guides every atom's motion. Even as galaxies collide or black holes merge, the field adjusts, redistributing energy to keep the universe's grand geometry consistent. It's like a conductor you never see, keeping time for an orchestra that spans eternity. A fringe notion arises from the edge of your mind. What if quintessence can interact with dark matter? A few daring papers suggest the two might exchange energy, dark matter gradually feeding the field that drives acceleration. If true, then dark energy could literally consume darkness to grow. The metaphor is too good not to enjoy, though the math makes most physicists wince. Still, you have to admire the audacity. It's the kind of idea that keeps conferences interesting and late-night coffee flowing. You look back at the cosmic web and notice how differently it feels now that you've given the vacuum a heartbeat. Expansion isn't mechanical anymore, it's organic. The universe evolves not just in structure but in temperament. It has eras of growth, calm, and possibly decline. The cold abstraction of lambda becomes something almost emotional, a field that changes its mind. You let yourself imagine the far future under this model. Quintessence continues to weaken, its push diminishing decade by cosmic decade. Galaxies hold their places, clusters stabilize. Expansion slows to a crawl, then settles into near stillness. Stars continue to burn, but the night sky stays familiar for far longer than in the chill scenario. Civilizations, if any survive, might even notice that distant galaxies no longer redshift as fast. They'd build telescopes, measure, argue, and perhaps smile at the realization that the cosmos itself is aging into tranquility. Of course, the field could change direction instead. Some potentials predict oscillations, dark energy that waxes and wanes, causing mini-accelerations followed by pauses. The universe might pulse, not eternally expanding but breathing in soft rhythms across tens of billions of years. One can almost hear it, a slow cosmic heartbeat echoing through time. Historians still argue whether nature really needs such complexity. Simpler models fit the data well enough, and Occam's razor is sharp. But maybe simplicity isn't the universe's priority. Maybe it enjoys texture. Maybe quintessence, if real, is the way the cosmos keeps improvising, never static, always playing a new variation on the same grand theme. You drift through that thought like a note fading in a long piece of music. If the vacuum can evolve, then so can fate itself. And if dark energy has a life cycle, perhaps it's not the villain of cosmic expansion, but merely one phase in an endless transformation, the breath between beginnings. You glide onward through that notion of an evolving universe, through data streams and dust and deep silence, until the view fills with glittering machinery, telescopes, detectors, satellites, the patient eyes of humanity pointed outward. They're the ones trying to track a dying field, measuring whether that faint cosmic pressure really is changing its tune. The universe, to you, looks infinite, but to them it's a spreadsheet of redshifts, magnitudes, and statistical error bars. Romantic in its own nerdy way, you hover above a research complex on the Chilean plateau, where the air is so thin the sky seems closer, rawer. Inside the dome, astronomers stand in their oxygen masks, sipping coffee that tastes faintly of altitude. Their instruments are tuned to faraway galaxies, tens of billions of light years out, each one a fossilized moment in the expansion story. By watching those galaxies at different distances, they're effectively watching time itself unfold, checking whether the universe has always accelerated at the same rate. One of them adjusts the controls of a giant survey camera. On her screen, a cluster of supernovae appears, tiny dots marked in pale blue. The light from each explosion tells her not just how far away it was, but how fast the universe was stretching when it went off. She's hunting for subtle discrepancies, hoping to catch the moment dark energy wavered. Each flicker of light, a cosmic confession. Historians still argue whether this style of precision cosmology has turned astronomy from an art into an obsession. The Hubble tension, the mismatch between the universe's expansion rate measured nearby and that measured from the cosmic microwave background, has kept theorists arguing for years. Some say it's an instrumental quirk, others whisper that it might be evidence for evolving dark energy. The debate's polite on paper, less so over coffee. You drift through the data, through the humming laboratories where numbers pour in faster than anyone can interpret them. The Dark Energy Survey, a name both dramatic and literal, has spent years mapping the shapes of hundreds of millions of galaxies. Their alignments, slightly stretched by gravity along the way, reveal how cosmic expansion has changed over time. It's subtle work. The distortions are so faint that a miscalibrated lens could fake them. But that's the thrill. The whole fate of the cosmos might hinge on micrometers of precision. A quirky anecdote surfaces as you hover near their control center. One night, the automated telescope's weather sensor froze, falsely detecting clear skies, and the dome opened into a blizzard. The operators called it the universe rejecting surveillance. They saved the equipment, but the joke stuck. Maybe dark energy wants to keep its secrets. You leave the desert and soar into orbit, past satellites glinting in the sunlight. There's the Planck relic, now retired, its detectors cold and silent. And there, sleek, silver, still humming, is Euclid, Europe's new eye on the dark. Its instruments map the shapes and colours of galaxies up to 10 billion light-years away, cross-checking how their clustering patterns evolve. You glide beside it as it drifts in its L2 halo orbit, a sentinel halfway between Earth and the void. Inside, algorithms crunch numbers, comparing billions of data points to model universes, some with steady lambda, others with fading quintessence. If the real data prefer one shape of the curve over another, it might be the first whisper of change. Somewhere in that sea of statistics, the fate of everything hides behind the decimals. Historians still argue whether cosmologists should even be allowed to use words like fate. But out here, in the dark, it's hard not to. You dive deeper into another probe's line of sight, the Nancy Grace Roman Space Telescope, NASA's upcoming dark energy hunter. It's designed to map the sky in infrared, peering through dust and time to measure how galaxies and supernovae behave billions of years apart. Together, Roman and Euclid form a cosmic tag team, one measuring distances, the other shapes, both whispering to the same invisible field. A quick detour through history. When the original Hubble Space Telescope launched in 1990, no one even knew dark energy existed. 30 years later, telescopes are being built almost entirely to study it. It's as if the universe dropped one cryptic clue in the 1990s and humanity collectively decided to spend the next century decoding it. You can't help admiring that kind of persistence. You follow the photons themselves, watching as they leave ancient galaxies and travel billions of years through expanding space to hit those detectors. Each photon carries a timestamp, the scale factor of the universe when it left home. Add them all together and you get a history of expansion written in light. The question is whether that history's slope is constant, steepening or softening. Some researchers look for other ways to check. Gravitational waves, ripples in spacetime itself, can act as standard sirens. When two neutron stars collide, they send both light and gravity ripples across the cosmos. By comparing how each travels, scientists can test whether spacetime's expansion behaves differently for different kinds of waves, a possible sign of evolving dark energy. It's elegant, dangerous work. One misplaced decimal, and you've redefined the fate of reality. You picture the labs where this analysis happens. Whiteboards covered in symbols, graduate students asleep on beanbags, someone's cat photo taped next to the phrase W open parenthesis. A close parenthesis equals W sub 0 plus W sub A open parenthesis 1 minus a close parenthesis. The function describing how dark energy's strength might change over time. A quiet mantra, half poetry, half mathematics. Outside, space keeps doing its thing, stretching, glowing, cooling, while humanity tries to read its diary. The latest data hint, ever so faintly, that dark energy's pressure might be easing. Not enough to declare victory, but enough to feel the hairs on your cosmic neck rise. A 2 sigma result here, a mild preference there. Science speak for something's up. A quirky press conference joke floats past your memory. A cosmologist says, "We found evidence that dark energy could be changing." Another asks, "By how much?" The first smiles, "About 1 part in eternity." Still, even 1 part might matter. If dark energy weakens with time, it would rewrite every textbook, every simulation, every future. It would mean the universe isn't heading for endless isolation, it's evolving toward reunion. You hover in the silence beyond all telescopes, looking back toward Earth. Down there, people sleep under expanding skies, unaware that their descendants might live in a cosmos that one day slows its drift. The faintest of all changes written in the geometry of everything. You smile because the chase isn't just scientific, it's profoundly human. Curiosity itself might be the universe's way of looking inward, checking whether its own heart still beats. And tonight, in the hum between galaxies, that heart sounds like it's slowing. You leave behind the glow of observatories and drift into something quieter. The pure geometry of space-time itself. Out here, where the cosmic microwave background fades to a whisper, you can almost feel the fabric of the universe breathing. It's not static. It ripples, bends, trembles ever so slightly under the weight of mass and the tug of energy. You float through those ripples, tiny wrinkles left by cataclysms that happened billions of years ago. Black hole mergers, neutron star collisions, the faint echoes of the Big Bang itself, and somewhere beneath it all, an almost imperceptible pulse, dark energy's signature, if it leaves one at all. You drift alongside a gravitational wave, a subtle distortion of reality propagating through everything. It's faint. By the time it passes you, its amplitude is smaller than a proton's width. But it carries information, how mass moved, how space-time responded, how the universe's expansion stretched its rhythm as it travelled. If dark energy really is fading, then even these waves might tell the tale. The idea isn't new. Back in the 2010s, when LIGO first detected gravitational waves, cosmologists realized they'd gained a new ruler. As these ripples travel across the expanding cosmos, they stretch with the very space they move through. Compare their frequency when emitted to when they arrive, and you can read the expansion history like a vinyl record's groove. In principle, if the expansion is slowing, the rhythm should shift, ever so slightly but measurably. Historians still argue whether gravitational waves should be called sound or light. Einstein himself alternated between describing space-time as an elastic sheet and as a kind of fluid, depending on which metaphor offended fewer mathematicians. Either way, you can't help noticing the irony. The universe has been vibrating since its birth, and only recently have humans built instruments sensitive enough to hear its hum. You imagine the next generation of detectors, massive spaceborne interferometers like LISA, with 3 spacecraft trailing Earth in orbit, separated by millions of kilometers of laser-linked emptiness. You float between them as beams of light bounce back and forth, measuring distances to picometers. Lisa's job will be to listen for the lower, slower waves, signals from supermassive black holes colliding in distant galaxies. Each wave that passes will have crossed billions of light-years of expanding space, and its frequency will carry the imprint of whatever dark energy was doing along the way. One quirky prediction you remember from a conference talk. If dark energy is decaying, then distant gravitational waves might arrive ever so slightly earlier than expected, as though the universe's fabric had lost a bit of elasticity over time. It's such a tiny effect that you'd need thousands of detections to be sure. Still, the theorist on stage grinned and said, "If we ever measure that drift, it means we're literally hearing the universe slow down." You drift on through those invisible ripples, feeling the strange intimacy of a cosmos that hums with its own structure. In some ways, gravitational waves are the truest record of reality. They don't scatter, don't fade, don't forget. Light can be absorbed, dust can distort it, but a space-time ripple just keeps going. Maybe dark energy leaves fingerprints here, tiny phase shifts in the cosmic orchestra. Historians still argue whether we'll ever separate that faint signature from noise. The math is brutal. But the dream persists, to detect not just gravity's echo, but the changing tone of the vacuum itself. And the quantum side of things? That's even murkier. You drift further inward, into thought experiments and probabilities, the domain where space-time itself flickers. Quantum field theory insists that the vacuum isn't empty at all. It seethes with virtual particles popping in and out of existence, a foamy soup of fluctuations. Every point in space is a restless crowd. If dark energy comes from that quantum foam, then perhaps fading dark energy means the foam itself is settling, calming as the universe ages. You picture it, the vacuum as a kind of quantum ocean, its surface once stormy with high-energy waves during the Big Bang, now smoothing over time. Maybe expansion itself acts like friction, draining the vacuum's turbulence. The longer space stretches, the more evenly it spreads its own energy, like cream settling into stillness. A fringe theory comes to mind, an idea that the cosmic expansion might actually bleed energy away from the vacuum into gravitational waves, microscopic ripples you could never detect but that collectively cool the universe's underlying field. If true, dark energy's fade could literally be the universe ringing down, like a bell losing its last vibrations. You hover in the quiet and imagine that sound, the aftertone of existence. You can't hear it, of course, but your thoughts fill in the gap, a deep, endless note, half gravity, half memory. Maybe the entire cosmos resonates with it, maybe we do too. One quirky anecdote. During a 2024 symposium, a physicist proposed that quantum fluctuations might not just drive dark energy, but also record the universe's history in their interference patterns like spacetime's version of a vinyl groove. Her colleague raised a hand and said, "So the universe is a record player?" She smiled. "Yes, but the record's playing itself." The room laughed, but you suspect she was serious. If dark energy fades, perhaps those quantum grooves will grow shallower, smoother, quieter. The vacuum would approach a true ground state, still, stable, finished. Expansion would slow, and the universe might become transparent to its own past. In that calm, even gravitational waves would propagate unchanged, unwarped by further stretching. The cosmos would finally fall silent, except for the occasional ripple from an ancient merger echoing through infinite stillness. Historians still argue whether silence is even a valid metaphor for physics, but it fits. You float through this imagined future, where the last gravitational wave passes you, like the last sigh of a great symphony. No noise remains, no motion to stir new ripples, space is relaxed. And yet, that silence doesn't feel empty, it feels earned. The universe, having spent eons expanding, stretching, vibrating, finally finds equilibrium. The song ends not because the orchestra faltered, but because the music was complete. You let that realization settle around you like cool water. Maybe the fading of dark energy isn't a decay, but a resolution. Every ripple that's ever crossed space, every photon that's ever stretched, has been part of a long cosmic chord, and now, slowly, it fades into harmony. You drift in that peace for a while, unsure whether you're hearing the universe's last note or its first rehearsal, for whatever comes next. You float in that quiet harmony for what feels like forever, until a new image unfolds ahead of you, a ledger glowing faintly in the void. Rows of numbers, neat and infinite, drift across the darkness like constellations that learn to count. You realize you're looking at the universe's cosmic balance sheet, its budget of energy, matter, and motion. Everything that has ever existed fits somewhere on this grand accounting page. For all its mystery, the cosmos is surprisingly economical. Every photon, every proton, every flicker of dark energy adds up to exactly the total allowed by the laws of physics. No overdrafts, no missing cents. For the moment, the numbers read something like this: 68% dark energy, 27% dark matter, and a humble 5% ordinary matter. The kind that makes stars, planets, and the coffee you forgot about on your desk. That's today's cosmic pie chart. But if dark energy is fading, then those percentages aren't fixed. They're shifting quietly behind the scenes. Imagine the pie slowly changing flavour, the slice of dark energy shrinking bit by bit while gravity and matter regain a little more influence. It's slow work, almost imperceptible, but over cosmic time it could rewrite everything. Historians still argue whether the first cosmic inventory was a triumph or a warning. Back in the early 2000s, when data from the WMAP satellite came in, scientists finally had a number for how much dark energy there was. It fit the model so perfectly that some joke the universe must have read the textbook. Others weren't laughing. If it's 68% and we don't know what it is, one physicist said, then the universe just told us we understand 1/3 of existence. You glide between the floating numbers, tracing their delicate interplay. Each component of the cosmos evolves at its own pace. Radiation fades quickly, matter thins more slowly, dark energy stays nearly constant, or used to. If its density now decreases even slightly, the balance of power shifts. The curves on the cosmic energy density chart start to bend, their intersections moving toward the future. You can almost see it, the dark energy line dipping, the matter line flattening, the faint resurgence of structure forming on the horizon of time. Gravity, that old accountant, always gets the last word. A quirky thought experiment surfaces. Imagine the universe as a cosmic economy. Matter is the capital. It builds galaxies, stars, and life. Dark matter is infrastructure, the invisible scaffolding that keeps everything in place. Dark energy? That's the mysterious investor inflating everything's value. If it withdraws its funding, the market crashes. In this case, not down but inward. You hover near a patch of simulated space, where the dark energy density parameter omega lambda is artificially reduced from 0.68 to 0.5. The expansion slows visibly. Large-scale structures, filaments and clusters, start to thicken. Galaxies cling more tightly to their neighbours. The cosmic web brightens with rekindled gravity. The universe looks less like a dissolving mist, and more like a tapestry being rewoven. Historians still argue whether this kind of rebalancing could ever happen naturally, or if it violates conservation laws. The math allows it if dark energy is tied to a field that can transfer energy elsewhere, but the details remain maddeningly speculative. The universe's books are balanced, yes, but we still don't know the accountant's name. You think of how fragile the present-day ratio really is. Just a few billion years ago, dark energy was weaker compared to matter. 5 billion years hence, if it continues to fade, it might drop below the threshold where acceleration dominates. The universe could transition back into a matter-dominated phase, one where gravity calls the shots again. You could call it a cosmic midlife crisis, settling down after a reckless youth of expansion. A mainstream historical fact floats through. In 2013, data from the Planck satellite refined the cosmic composition to astonishing precision, confirming that dark energy dominates. The announcement was front-page news, but what stuck in people's minds wasn't the measurement itself. It was the emptiness it implied. Most of the universe is invisible, untouchable, and possibly temporary. Then you recall a quirkier bit of trivia. One research group once tried to express cosmic composition using food analogies. The universe, they said, is 2/3 dark chocolate, 1/4 dark roast, and a sprinkle of salt. The joke made it to a conference poster. Even in the face of existential physics, scientists can't resist a snack metaphor. You glide along one of the luminous lines of this grand ledger, watching it tremble slightly where uncertainties still linger. The parameters have errors, margins, assumptions. If dark energy truly fades, those lines won't stay straight. They'll curve downward, signaling that the vacuum itself is relaxing. It's not dying exactly, just settling into a quieter equilibrium. From your vantage point, it looks almost organic. The numbers shift like the colours of an old forest, green to gold to grey, a living system that ages. You start to realise that even cosmology, with all its precision, is telling a story of impermanence. If the dark energy fraction keeps decreasing, say from 68% to 60, then 50, then galaxies will stop accelerating away and might begin to drift closer again. On unimaginably long timescales, the universe could start recycling its contents, condensing into dense pockets of new activity. Black holes could merge into colossal structures, and perhaps in the farthest future, when enough of that energy has drained, a new burst of creation might occur, a local bounce inside the grand ledger, a cosmic side hustle in accounting terms. Historians still argue whether the term fading is poetic or precise. The data can't yet tell if the dark energy density truly changes with time, or if it only appears to because of local effects. Maybe we're just a small region where the vacuum value happens to dip, a cosmic coincidence. Or maybe this is the beginning of the universe's financial correction. You hover over the balance sheet's lower margin, where a new line begins to form, one labelled omega lambda t, a variable, not a constant. It's faint, tentative, but there it is. The suggestion that the vacuum's power isn't fixed after all. That symbol, small and cautious, could rewrite everything. You imagine the accountants of the far future, post-human astronomers if such beings exist, recalculating the numbers and realizing they live in a cosmos where expansion has nearly stopped. They might look back on your era, the age of acceleration, as a youthful exuberance, a brief phase of cosmic overspending, and you, hovering here between the ledgers, realize the math tells a surprisingly gentle story. The universe isn't running out of energy, it's redistributing it. Balance isn't collapse, it's completion. The lights of the balance sheet dim until only one number remains, pulsing softly in the void. 1. The total energy of everything, constant, conserved. The cosmos might change shape, fade, reconfigure, but the sum never wavers. You drift away from the ledger, the numbers dissolving behind you like the afterimage of stars. Somewhere, the universe is still balancing its books, still making sure the story adds up. You leave the cosmic ledger behind, letting the numbers dissolve into blackness and drift into a quieter patch of the universe. Here, light is scarce, but not gone. The galaxies shimmer faintly in the far distance, scattered like embers across an ocean of space. You realize you've arrived in the future, the slow, cooling epoch where stars are rarer, skies are dimmer, and life, if it still exists anywhere, must cling fiercely to warmth. Welcome to a universe with less dark energy and more patience. If the fading continues, if the push that drives expansion weakens year by year on cosmic scales, the galaxies will stop sprinting away from each other. Their redshifts will plateau. Gravity, cautious and enduring, will begin to reassert itself. The cosmos won't collapse overnight, of course. This is no sudden doomsday. But the runaway acceleration will ease, like a long exhale finally meeting still air. The result? A cosmos that feels calmer, denser, more habitable, in a strange way. You drift toward one of the surviving spiral galaxies, familiar but changed. Its arms are faded, its gas nearly spent, yet it still glows with the dull orange light of ancient stars. Around one of those suns spins a rocky world, cold but stubbornly alive. You descend through its thin atmosphere and find an observatory perched on a frozen plain. Inside, descendants of something human, biological, mechanical, or both, peer through instruments at the sky, studying a universe that's noticeably slowing. They can see the difference now. Their sky is darker than yours was. The Milky Way has long since merged with Andromeda into a vast elliptical galaxy, a glowing city of ancient red stars. Its light spills across the heavens, soft and coppery. But unlike the lonely, expanding universe you left behind, these observers still see other galaxies nearby. Fading dark energy means the cosmic horizon no longer shrinks. More of the universe remains visible. The night is wide again. a mainstream historical fact glimmers in your mind. When the first humans looked up, the Milky Way was the only galaxy they could see with their naked eyes. Billions of years later, future astronomers may find themselves in a similar position, but for the opposite reason. In one possible future, dark energy isolates every galaxy. In another, if it fades, the universe stays social a little longer. You drift into their data center, a place of quiet reverence. Their computers hum softly, slow quantum processors built for timescales longer than civilizations. The researchers plot redshift curves and expansion parameters just like their ancestors once did. And for the first time in cosmic history, the numbers are dropping. Expansion isn't accelerating anymore, it's coasting. They whisper about it in cautious tones, the way early astronomers once whispered about heliocentrism. Historians, those that still exist, still argue whether this change marks the beginning of the universe's second half or merely the end of its first. Either way, you can feel the shift. Space feels thicker somehow, less hurried. You glide above the planet's frozen surface. Thin wisps of aurora dance across the poles, faint green curtains powered by the last magnetic flickers of its cooling core. The inhabitants, these distant descendants, have adapted. Their energy comes from fusion reactors that mimic the stars that no longer burn in their sky. They've learned to store starlight, not just witness it. You catch a fragment of their language, projected through the observatory's radio beacon. It's not words exactly, more a tone, a sequence of harmonics that convey emotion as much as meaning. You recognize one pattern repeated, the sky slows, a quiet joke follows. Finally. They're the first beings to live in a universe that feels like it's resting. A quirky historical tidbit surfaces from your memory. In the early 21st century, scientists calculated the universe's cosmic temperature. Even empty space has one, the 2.7 Kelvin of the microwave background. In this future, that temperature has dropped further, but only slightly. If dark energy fades, the background cools more slowly, delaying the deep freeze by untold eons. It's as if the universe has thrown a blanket over itself, conserving warmth. You imagine what life might mean in such a slow cosmos. Stars are rare, but black holes remain, massive furnaces of time and gravity. Around them, civilizations could harvest Hawking radiation, drawing power from the edges of eternity. Some theorists in your era called these black hole farms. Others, more poetic, imagine them as the last hearths of creation. Historians still argue whether such distant futures are worth speculating about, but you can't help yourself. The vision is mesmerizing. A cosmos where the frantic expansion has ended, replaced by a patient glow. The galaxies are closer, their light less redshifted, their gravity reawakening subtle tides across the void. You drift through one of those voids now, and even here faint streaks of matter are visible, filaments that haven't thinned to transparency. They ripple slowly, like tendons in a sleeping giant. In a fading dark energy universe, those filaments might eventually tighten again, drawing matter back toward their nodes. The web that once expanded could, after trillions of years, begin to contract. From your distant vantage, you sense a new balance emerging, not the eternal stretch of the old accelerated epoch, but something cyclical, almost musical. Expansion and gravity in dialogue rather than conflict. Down on the planet, the observatory's descendants send out one last signal, a time capsule encoded in gravitational waves, broadcasting the story of how the universe once ran faster. It's their way of thanking the cosmos for slowing down enough to notice. You watch the signal spread, its ripples faint but persistent, weaving through the dark like a heartbeat through water. You can't help smiling at the thought that maybe, billions of years ago, humans did something similar, sent messages into the dark, hoping someone, somewhere, would listen long after they were gone. It's comforting to think the cosmos might be listening still. You glance back at the galaxy cluster glowing faintly behind you. Its light feels warmer now, closer. The void between things isn't so lonely anymore. Maybe this is what happens when the universe learns to breathe out and in at the same time. You can almost feel that rhythm yourself. A steady pulse beneath the silence, expansion softening, gravity returning, light persisting. The cosmos, in its twilight, has become gentle, and somewhere in that gentleness, life, stubborn as ever, keeps its vigil. You stay with those quiet descendants for a while, their observatories blinking like small eyes against the dark, and then you drift outward again. The cold air of the cosmos thickens around you, if air can describe something that's 1 hydrogen atom per cubic meter. Beyond their galaxy, the universe is still a whisper of motion, slower, steadier, tired, but not done. You move toward the next question the cosmos asks once acceleration fades. What becomes of knowledge when the light itself begins to end? For most of cosmic history, astronomers, whether human or otherwise, have been archivists of light. Every photon that reached them was a clue, an entry in the diary of the universe. But when dark energy weakens and distances shorten only slightly, the ancient light still matters. It's the only way future minds will know what came before. You float past one of their data vaults, a crystalline lattice suspended in orbit, storing centuries of observation. The beings who built it knew the stars would vanish eventually, so they encoded the history of brightness itself. Spectra, redshifts, whispers of expansion, all locked in transparent stone. Historians still argue whether their efforts are acts of science or acts of faith. In a universe where the sky dims millimeter by millimeter, building archives of starlight feels like lighting candles in a storm. Yet that's what intelligence does. It remembers, even when memory is all that's left. You drift along the vault's surface. Laser inscriptions shimmer across it, tracing the old laws. Hubble's constant, Einstein's field equations, the lambda symbol now crossed out with a graceful diagonal line, an equation retired with affection. Next to it glows a new symbol, something like a looping letter, Q, their shorthand for the dynamic fading field they've confirmed through eons of observation. Quintessence, they call it still, though the word has softened in their language. You can read their history in the glow. When the dark energy curve first began to decline, they noticed. At first they thought it error, then anomaly, then miracle. Over the next billion years, the data held steady. Expansion easing, structure thickening, the cosmic balance sheet tilting back toward gravity. They watched the galaxies creep closer in the night, slow enough that patience replaced thrill. Their textbooks began with the same sentence. The universe once ran away from itself, but now it listens to its own footsteps. You hover above their world and look at their night sky. It's astonishingly rich. Hundreds of galaxies visible to the naked eye, shining orange and red. The spectral lines are sharper now. Less stretching means less blur. Their telescopes, far smaller than those you knew, can resolve details unimaginable in your epoch. What humans once saw only through simulations, they see directly. Filaments twisting together, cosmic voids shrinking, clusters merging in slow grandeur. A mainstream historical fact drifts through your thoughts. In your time, scientists estimated that 94% of galaxies lay forever beyond our observable horizon, racing away faster than light could follow. In this future, if dark energy truly fades, that number drops. Horizons expand again. Distant galaxies re-enter the realm of the visible. The cosmos becomes knowable anew. A quirky note from their archives makes you smile. One of their philosophers suggested renaming the age they live in the era of rediscovery, since light from galaxies long lost to acceleration is gradually drifting back into view. Another proposed the long twilight, which sounded more dramatic and therefore won the vote. Scientists protested the melodrama. Poets cheered. You glide toward one of their education domes where young minds learn about the ancient accelerated era. Holographic displays reconstruct your epoch, the 21st century, with glowing blue lines showing galaxies rushing apart, arrows of expansion darting outward. This was the great stretch, a teacher says in tones both awe-filled and affectionate. We are what came after the rush. The students watch silently, as if they can almost feel the motion that once carried everything away. Historians still argue whether memory of acceleration will fade as thoroughly as the energy itself. Will future civilizations, millions of years hence, still understand what a redshift was? Or will they, living in a denser cosmos, assume the universe was always this gentle? Perhaps somewhere, a lone archivist will still whisper the old numbers: 13.8 billion years, 68% dark energy, 5% matter. Perhaps they'll speak them like a prayer. You drift past another research outpost, this one circling a quiet black hole. The hole emits a faint halo of Hawking radiation, power for their instruments. They're using it to measure gravitational echoes from ancient mergers, hoping to find whether the cosmic expansion's slowing has altered the wave's spacing. Even now, they're looking backward through gravity itself to confirm that dark energy truly continues to fade. Their motto etched on the hull reads, "Listen, because the silence changes too. Down below, life persists. Artificial suns orbit the inner planets, powered by controlled fusion. The descendants of old civilizations farm light the way their ancestors once farmed soil. They live long, think slowly, and consider the universe not a mystery but a companion aging alongside them. They've learned something that their predecessors only theorized, that knowledge itself has a lifespan. Data decays, memory degrades, but curiosity endures. A quirky cultural custom has taken root among them. Each cycle, when their largest moon crosses the planet's shadow, they hold what they call the illumination pause. For one night, no artificial lights burn. They sit beneath the raw sky, cold, immense, honest, and recite from memory the known constants of physics, like a litany. Then they add the newest value of W, the equation of state ratio, now inching towards zero as dark energy ebbs. It's their way of saying, we are still counting, the universe is still changing. You listen to their recitation from orbit. The voices drift upward through thin air and vanish into the dark. For a moment, it sounds like a choir of scientists singing lullabies to spacetime. Historians still argue, somewhere in their data archives, whether knowledge has an endpoint, whether a universe that eventually stops expanding will still support the pursuit of understanding. But looking down, you can tell they already have their answer. The act of learning has become their form of survival. As you drift away, you catch a glimpse of their final inscription carved on the side of the vault. When light ends, thought begins again. And just like that, the vault glows faintly, its stored starlight shining a little brighter against the slow, gathering dark. You drift further into the future, so far in fact that time itself feels syrupy, stretched thin but not infinite. The galaxies are dim embers now, the cosmic temperature a whisper above absolute zero. Expansion has nearly halted. The great outward push that once defined everything has dwindled to almost nothing, and time has become heavy. You feel it like gravity in your thoughts, dragging every second into an eternity. This is the slow age, the era after motion. The universe doesn't race anymore, it lingers. You pass through what's left of the cosmic web, its filaments no longer bright and busy but dense with ancient stars clumped close for warmth. Gravity has spent trillions of years gathering the stragglers. Clusters that once sprinted away have now begun to drift together again, pulled by the faint but unrelenting hand of attraction. In the silence, their collisions are symphonies of invisible power. Black holes merging, galaxies collapsing inward, matter reuniting with matter. You sense it everywhere. A hush, but not an emptiness. The universe hasn't died. It's just slowed so profoundly that change happens at a glacial pace. Whole centuries pass between cosmic heartbeats. The starlight you see isn't new, it's ancient, recycling through gravitational lensing and reflection like the echo of a sunset that never ends. Historians still argue whether time can slow in any meaningful way. Technically it doesn't. Clocks tick as they always do, bound by local physics, but perception is another thing entirely. When the expansion rate approaches zero, the fabric of spacetime stops stretching. Every photon, every orbit, every rotation of a dying world becomes part of a single frozen choreography. The cosmos enters what some future thinkers call the era of rest. A mainstream historical fact surfaces. Even back in your era, astrophysicists predicted that in 10 trillion years, star formation would end. By 100 trillion, most stars would be faint red dwarfs, their fusions exhausted. Now, here in the deep twilight, that prediction has come true. The few remaining suns are small, long-lived, and red. Tiny beacons scattered through a thickening dark. They burn not brightly, but stubbornly. You drift past one such star system. The central dwarf glows dimly, its planets tidally locked so that one hemisphere bakes gently, while the other freezes forever. On the twilight line between them, where day meets night, small colonies of life still persist. They're slow too, their metabolisms adapted to the crawling pace of a tired universe. They measure time not in seconds, but in eons. For them, the motion of a nearby galaxy across the sky is a story told over generations. One quirky fragment of their culture reaches you through a decaying signal, a song recorded on a thin film of diamond. It's a hymn to gravity, set to frequencies you can almost feel rather than hear. The translation scrolls across your mind. When the light grows cold, the pull remains. The dark is patient, and so are we. You smile. Even here in this weary epoch, consciousness sings. You move on. Space no longer feels like a void. It feels viscous, like you're gliding through the honeyed flow of deep time. The last black holes dominate the landscape now. You pass one, enormous and perfectly still, surrounded by a faint accretion disk glowing with Hawking radiation. Over unimaginable stretches of time, it will evaporate particle by particle, returning its mass to the universe as faint heat. If dark energy truly has faded, that heat will linger longer than once expected, trapped in a cosmos no longer expanding fast enough to scatter it. You realize what that means. Warmth will persist. The final chill, the heat death once feared, may never arrive. Instead, the universe hovers in a near-still equilibrium, not frozen, not collapsing, just resting. Historians still debate whether such balance is stable or temporary. Could quantum fluctuations, small as they are, eventually tip the scales? Could a ripple in the field restart expansion or trigger collapse? The equations allow both, though the probabilities stretch beyond imagination. To the beings of this age, probability is philosophy. They no longer speak of when or if, only of tendencies. You sense them faintly. Intelligence is no longer biological, perhaps no longer individual. They've merged into vast networks of computation and memory, their processors woven from cooled matter and stable black hole remnants. They think slowly, not because they must, but because there's no rush. Their communications ripple through the cosmos like long sighs. One of their transmissions brushes your awareness. We have measured the acceleration again. It is zero within our limits. Space rests. There's something tender in the way they say it, as though they're proud of the calm their universe has achieved. You float deeper into the dark toward a region of space where nothing moves. Literally nothing. The distance between any 2 points has remained unchanged for eons. It's uncanny. Without expansion or contraction, coordinates lose meaning. Up and down vanish. Even direction feels optional. You're inside a universe that's paused mid-breath. A quirky theory from your own era pops into memory. Physicists once proposed that time itself might emerge from change. If nothing moves, nothing happens, and time ceases to flow. In this place, you can almost believe it. You feel suspended, not frozen, but timeless, as if you've stepped outside the script entirely. Perhaps that's what happens at the edge of the universe's long life. Not death, but transcendence. The cosmos doesn't end. It simply stops needing to update. The information is complete, the energy distributed, the equation satisfied. A final frame held perfectly still. And yet, from somewhere deep within that stillness, you feel a tremor. Faint, but undeniable. A fluctuation perhaps in the old vacuum field. Maybe just a ripple of quantum chance, or maybe the whisper of the next beginning. Historians still argue whether any such tremor could ever grow. If dark energy has truly reached zero, any spark of new expansion would require imbalance, entropy reversing, symmetry breaking. Impossible by current physics. But the universe has never been particularly obedient. You imagine it, a tiny pocket of space-time where the field stirs again, where the pressure of the vacuum rises just enough to push outward. Not a new Big Bang yet, just a murmur of one, a seed of tomorrow in the stillness of tonight. For now, though, that's all it is. A hint, a heartbeat, a maybe. The cosmos remains quiet, its stars dim, its time viscous and slow. You hover there in the calm, listening for motion. And just when you start to think that silence is forever, you swear you hear it again. The faintest hum, like the memory of expansion tuning up for another song. You stay there in that syrupy calm, holding your breath with the universe, and the faint hum beneath everything won't quite fade. It's more suggestion than sound, a pulse hidden in the dark fabric. If dark energy has died entirely, if its value has at last drifted to zero, then what you feel should be impossible. But impossibility has never stopped the cosmos before. You look out across what remains of creation. Galaxies have merged into swollen clusters. Clusters have dissolved into black hole constellations. Every horizon has blurred with time until the sky is a single wash of faint copper. The temperature of space sits just above nothing, 10 to the minus 30 Kelvin, maybe less. Energy moves sluggishly, photons crawling like old snails, yet something underneath that stillness trembles, like a sleeping animal twitching in its dreams. Historians still argue whether a completely zero dark energy universe could ever be stable. The math says yes, flat space, no acceleration, eternal rest. But quantum mechanics, mischievous as ever, refuses silence. The vacuum still seethes, if only faintly. Tiny fluctuations appear, borrow energy, vanish again. Most cancel out, a few do not. And over time, unimaginably long time, those survivors can build into a ripple large enough to matter. You drift closer to one. It's minuscule, smaller than a proton's shadow, a flicker in geometry rather than matter. But it curves the space around it ever so slightly, like the first breath of wind in a room sealed for ages. The local metric shifts. Expansion begins again, but only here, only within a bubble a few light years wide. Inside it, space stretches by a fraction of a fraction. The ripple eats the stillness the way fire eats oxygen. You watch it expand. Slow at first, then faster. The bubble doubles, then doubles again. If gravity can't stop it, and there's nothing left massive enough to try, it will keep growing, pulling more of the dormant universe into motion. It's a newborn patch of space-time, raw and radiant, still unaware that it's repeating an ancient act. You realize what you're seeing. Not collapse, but ignition. A quirky historical fact flashes across your mind. In the 1980s, some cosmologists toyed with vacuum decay scenarios, where a false vacuum could tunnel to a lower energy state, creating a bubble of new physics that expands at light speed. It was meant as a cautionary tale, a one-way ticket to oblivion. Yet here it is again, wearing the opposite face. Creation instead of destruction. The vacuum hasn't decayed downward, it's bounced upward. A new high-energy pocket blooming out of the ashes of calm. You edge closer. The boundary of the bubble glows with unimaginable energy, where the new space-time rubs against the old. There's no sound, but the vibration is real, a texture that shakes thought itself. Inside, everything resets. Constants shift, forces realign, gravity and light reacquaint themselves, old colleagues meeting for the first time again. A flash, then inflation. Space multiplies, faster than comprehension, erasing the memory of the universe that birthed it. You hover outside, unable to cross. The wall between epochs is absolute. From here, the bubble looks like a tiny star blooming in infinite night. From the inside, it would look like everything. Historians, if any could witness, would still argue whether this counts as the death of the old universe or the birth of a new one. Maybe both, maybe neither. If dark energy's final act is to die, and then resurrect itself as expansion again, then the cosmos is caught in an endless self-reference, every end containing its own beginning, every void pregnant with another spark. You think of it less as a circle, and more as breathing that never quite stops. The surrounding space begins to buckle as the newborn inflation pulls matter, or what's left of it, toward its glowing heart. The black holes that dominated for eons crumble into radiation, feeding the fire. The numbers shift again. Density, curvature, constants. Inside the bubble they may be unrecognizable. Perhaps new kinds of particles form there, new laws of motion, a new speed of light. And if anyone ever evolves there, they'll look back and see a big bang, never knowing it was just one of many, each born from the tired silence of the last. A fringe tidbit from an old quantum gravity workshop surfaces. One theorist once joked that the universe might have reincarnation anxiety. It keeps recreating itself out of habit because it can't stand still. Everyone laughed, then paused, realizing the math didn't rule it out. You laughed too, softly. Eternity with stage fright. How human. You watch the growing brightness until it fills your view. The edges of the old cosmos crumble, devoured by this fresh inflation. Space is expanding again, but not yours anymore. You remain in the thin rain of the former universe, the quiet shell left behind when the new bubble took its first breath. It's cooling fast. Within moments, or eons, time has lost its meaning. The outer void will fade to true zero. No fields, no motion, no anything. The final ledger closes, and then, somewhere else inside that radiant bubble, a new timeline begins. Temperatures soar to trillions of degrees, quantum fluctuations shape new forces, the first particles condense. It's the Big Bang all over again, but with different numbers, a new cosmic constant, perhaps larger, smaller, or reversed. You can almost see it through the haze, tiny sparks forming nuclei, light scattering, structure seeds forming in chaos. Another chance, another story. You realize that if dark energy can die, it can also be reborn. Maybe that's the secret the cosmos has been whispering all along. It isn't a straight line from explosion to silence. It's a loop of curiosity, an endless feedback of beginnings learning from their own endings. The universe dreams, wakes, and dreams again. The hum you felt before swells until it fills you entirely, not a sound, but the memory of creation itself, repeating. You watch the new cosmos bloom brighter, faster, younger, until your vision dissolves in its light. And somewhere inside that blinding white, someone else, some future being, will one day float in the dark and wonder if dark energy might fade, and what happens when it's gone. You stay with that flash until it fills everything, white turning gold, gold turning blue, then fading back into darkness. The newborn universe expands beyond you, swelling faster than thought, its edges unreachable, its inside unknowable. You've just watched one reality give birth to another, but as the light fades, you realize something quieter remains, a kind of echo, soft and endless. It's not the sound of the new cosmos growing, it's the afterglow of the old one, your universe, settling into stillness beyond the reach of its successor. Here, at the edge of everything, the vacuum is truly empty for the first time. There's no field, no pressure, no potential energy waiting to ignite again. The last traces of the old geometry flatten, cooling into silence. This is what it means for dark energy to be gone. The universe, the one you knew, no longer pushes or pulls, it simply is. Space has stopped expanding, time has stopped stretching. There's no acceleration, no deceleration, no change at all. It's a stillness so complete that it almost feels alive, like a thought frozen mid-sentence. You drift in that quiet. Your movement slows too, not because of resistance, but because there's nowhere left to go. Every direction is the same. The phrase, "end of time," feels cliché until you're standing inside it. Historians, if any could speak now, would still argue whether such a final equilibrium counts as existence. Some would say the universe persists, even motionless, as pure geometry, a timeless sculpture of space-time. Others would insist that without evolution there is no being, only memory. But both sides would miss the poetry of it. The end isn't destruction, it's completion. You let your senses expand, and you start to see traces, ghosts of what used to be. The faint geometry of clusters long dissolved, the soft impressions of gravitational wells, the echoes of once brilliant quasars. The universe keeps its fingerprints. If someone, or something, ever recreated these patterns, they'd have a perfect fossil record of everything that ever happened. The quiet beyond expansion is not erasure, it's remembrance. You think about how every cosmic phase has mirrored something human. The fiery beginning, the chaotic middle, the cooling and fading, each a metaphor for creation, growth and rest. Maybe this last phase, this frozen calm, isn't a death at all. Maybe it's contentment. You float for an unmeasured age, feeling how smooth space has become. Without dark energy or gravity to warp it, space-time relaxes into perfect flatness. It's a condition the universe hasn't known since the first instant after the Big Bang, when everything balanced exactly on the knife's edge of potential. Full circle. Then faintly, you sense the bubble you watched before, the new universe, still expanding in its own domain, unreachable from here. Its light doesn't cross the border, physics forbids it. Yet somehow, you know it's there, humming like a chord just out of earshot. The multiverse may not be a place in any literal sense, but you feel the continuity, the handoff from one cosmic age to another. A mainstream historical fact surfaces in your memory. Some interpretations of inflation theory suggest new universes form endlessly, each with its own constants, its own vacuum energy. Most of them expand into oblivion, but a few might stabilize, producing stars, life, and consciousness. Maybe that process has always been happening, and you've simply followed one full cycle from beginning to end, and beyond. You smile, or at least think the thought that would become a smile if faces still meant anything. The question you began with, what happens when dark energy fades, has answered itself, and yet left you with something better than an answer: perspective. A quirky detail rises unbidden. An old 21st century physicist once quipped that the universe is the ultimate procrastinator. It will never truly stop. It'll just take longer and longer to do less and less. Out here, at infinity, you finally understand. The cosmos didn't stop to die. It stopped because it had done everything it needed to. You let your awareness dissolve into what's left. Smooth, eternal, neutral. No temperature gradients, no entropy to increase. Perfection through uniformity. The cosmos at peace with itself. And yet, deep down, you can't help noticing that perfection is unstable. It's too symmetrical, too precise. Quantum mechanics abhors perfection. Somewhere, inevitably, a fluctuation will rise again. An imbalance, a spark, a new asymmetry to begin another story. You can't see it, not yet, but you can feel the probability. Eternity is patient, so you wait. The darkness around you isn't frightening anymore. It's gentle, welcoming, the last exhale after an infinite sigh. The memory of galaxies, of stars, of the blue marble called Earth flickers faintly, then fades. Not lost, just folded into the fabric, part of the pattern that will inform whatever comes next. Maybe this is how universes dream. You close your eyes, or whatever serves for them now, and imagine the first flash of the next creation. Somewhere, a tiny ripple in nothingness will grow until it fills the void with light, heat, and motion once again. Somewhere, photons will learn to dance, gravity will carve the stage, and atoms will find the courage to assemble into life. Somewhere, someone will look up at their night sky and wonder what holds it all together, and whether that something will last forever. You smile again at the thought. They'll call it dark energy. They'll measure it, argue about it, name it after their ignorance. And one day, they'll notice it fading, just as you did, and ask what happens when it's gone. And the universe, as always, will answer with silence first, then with another beginning. You listen to that silence now, deeper than thought, until it becomes almost a whisper. All endings are openings slowed down, and somewhere beyond sight a new spark flickers. The lights return. The story begins again.